Hello everyone. My name is Urvi and I'm a software engineer at Microsoft. And I welcome you to this 5-part series by Scalar where we'll be covering linked list data structure in C++ programming language end to end. Here we'll learn about what is linked list data structure, how it's different from arrays. We'll solve some easy level questions on it, then we'll move on to medium level questions, and we'll also cover some hard level questions on this data structure. Post which we'll cover the variations of linked list, that are doubly linked list and circular linked list. So that after covering this full course, you should be able to solve any coding problem on linked list data structure. So let's get started. So in this first lecture, we'll be starting with what exactly is linked list and why are we studying linked list. What are some challenges that linked list is solving that are faced when we are implementing arrays? And we'll see some basic operations on linked list like insertion, deletion, updation, traversal, and in the end we'll solve some really easy level questions on this topic. So let's get started first of all with what is linked list. In very layman language, I can say linked list is a linear data structure that is used to store a list of items. Okay, it is a linear data structure that is used to store a list of items. Now, I can say the same thing about an array as well. An array is also a linear data structure which stores a list of items. But linked list in some ways I can say is better than arrays. Let's see how. Now there are some challenges that we face when we implement arrays. Okay, what are some challenges? First of all, arrays are of static size. What does this mean? This means that whenever I create an array, I have to specify the size of the array, and then after creating the array in code, I cannot modify its size. So for example, let's take an example. For example, I want to create an array where I want to store the name of the students who enroll in the course. Okay, and for example, I create this array of size 200k, but the number of students who end up enrolling in the course is actually 250k. All right, so now what will happen? The array that I created of size 200k will get wasted. I'll have to create a new array altogether of the 250k size to accommodate all of the students' details. Or another example could be if the number of students who enroll are not more but less. For example, only 180k students enroll in the course. So then 20k of array size would be wasted for me because that would be just lying there idle, and I cannot decrease the size of the array once I've created it. Alright, so that's a challenge that arrays pose, that they have static size. Another challenge in arrays is their memory allocation, which is contiguous memory allocation. Now, what does contiguous memory allocation mean? This means that the memory that is allocated to an array, when I create an array in C++, that has to be present in a contiguous manner in my memory. So how is this a challenge? For example, just imagine that this is my memory, all right, and I need 100 MB of memory, or let's just talk in bits here or bytes here. Okay, for example, I need 100 bytes of memory, and in my memory I have some memory that is free, but one chunk of that memory is 20 bytes and another chunk is 80 bytes. So now you see I do have the amount of memory that I need to create my array, right? I do have 100 bytes of memory that is free, but can I create an array here? No, because the 100 bytes of memory that I need for my array has to be present in a contiguous manner. It has to be present as a block, as a single block of memory. Is that insertion, deletion in arrays is expensive. So once again, imagine we have an array, all right, where we have some numbers 1, 2, 3, 4 and 5, all right, and I want to insert an element 8 here, okay, right here after 2. Right here after 2. Now to insert an element in the middle of the array, what I'll have to do is, first of all, whatever elements will come after it, I'll have to shift those elements. So I'll have to shift 3, 4, 5 first, and then I'll be able to insert 8 here. The same way with deletion, if I want to delete 8, some element from the middle, I can't just delete this one. I'll also have to shift the elements that come after it. I'll have to shift these elements. Alright, and this is given if I have extra space. If I don't have extra space and I want to insert an element in my array, then I have to create a new array altogether. Right, and if I delete elements, then there will be memory wasted. So these are some challenges that are posed by arrays. Now, how is linked list solving this? So I told you that linked list is a linear data structure that is used to store a list of items. Now the difference comes in implementation. How is linked list implemented? Linked list implemented as form of memory blocks that are linked to each other. Memory blocks or blocks in memory that are linked to each other. So for example, I take some block of memory at some random address, okay, and I take some other block of memory at some other random address, and these blocks of memories are linked to each other, and that is why this is known as a linked list. Alright, so just imagine in memory we have random blocks of memory which are linked to each other, okay, and these blocks of memory are storing some values. So this is how linked list is implemented, and how is linked list solving the challenges that are faced in arrays. First of all, it has a dynamic size, meaning that when I create a linked list, I don't have to specify the size of the linked list, okay. I can just keep adding more blocks of memory, more elements to my linked list, or I can keep deleting whenever I don't need. So there will be no memory wasted, and also if I want to insert more elements in my linked list, I don't have to create a new linked list altogether. Alright, so linked list is of dynamic size. I can keep inserting elements, I can keep deleting elements as and when I need. Number 2, non-contiguous memory allocation. So like I said, these are memory blocks that are linked to each other. Now these memory blocks, they don't need to be present all together in a contiguous block of memory. They can be present at different addresses in my memory, and they can be linked to each other. Alright, how they are linked, I'll just tell you, but for now just imagine that these are blocks of memory at different addresses that are linked to each other. So we don't need a non-contiguous memory, so we don't need contiguous memory allocation here. Alright, and the third and last thing, the insertion and deletion here becomes non-expensive. Alright, so here if I want to insert any element in the middle, for example, I want to insert a new element here, after the second element, I just have to change this link. I just have to change this link. I'll remove this link and add new links here. So I'll be able to insert an element, so I don't have to move the other elements anywhere or shift them anywhere. Similarly, if I want to delete this element in the middle, so I can just create this link back and get rid of these two links and the element. So I've deleted now. So here again, none of the other elements have to be shifted, right? So insertion and deletion in a linked list become non-expensive for us. All right, non-expensive in terms of time and space complexity. So these are the three things that make linked list different from arrays and solve some of the challenges that are faced by arrays. All right, now let's discuss what is the building block of a node. So we've been talking about memory blocks, right? I've been talking about memory blocks in linked lists that are linked to each other. So you can imagine, you can call each of this memory block a node. All right, you can call each of this memory block a node. Now a node is made up of two parts. A node is made up of two parts. First is the value, all right, and this is the data that we are storing. This is the data we are storing, that we want to store in our data structure. And the second part is a pointer, okay, or let me call it next. What this is, the second part of my node, this is a pointer to the next node in my linked list. Okay, so this is how these nodes are connected to each other. Each node will have a pointer which will be pointing to the next, just the immediate next node in my linked list. Okay, so for example, I have a node here in which I am storing some value 1, all right, and I am also creating another node. I want to add a node to this linked list in which I have value 2. So for example, if this node is present as address 200, okay, I'm just taking an example here. If this node is present at address 200, so I'll have the address of the next node in the second part of my linked list. All right, so this is how I'll have these two nodes connected. Similarly, I can add another node to my linked list in which I have a value 3, and if this node is present at address 300, so I'll have 300 here, and this is how I'll connect this to this. All right, and this is my linked list. So a linked list is made of nodes. A node is made of two parts. First is the value part, the data that we want to store, and the second part is the next, which is a pointer to the next immediate node in my linked list. Now, how do I know where my linked list is exactly starting? Where is the first node? For that, we take help of another pointer called head pointer. Okay, so the head pointer tells us where my linked list is starting, and if I give you the head pointer of any linked list, so you'll be able to traverse all of the elements in my linked list, right? Because the head pointer will be the first node will be pointing to the second node, so I'll get the second node from there. From the second node will be pointing to the third node, so I'll be able to get to the third node from there, and so on. So if I'm just given the head of a linked list, I can traverse all of the nodes of my linked list. And how do I know where my linked list is ending? That is known because the last node in my linked list, in the last node of my linked list, the next value will be null. It will be a null pointer. Alright. So whenever the next part of any node is null, that means that is my last node in my linked list. Alright, so this is the example of a linked list. Let's try implementing this in code now. So for implementing a node, we'll create a class node. Alright, we'll be taking help of object-oriented programming here. Now I told you that my node will have two parts. Okay, first is the value part. So let's assume that the value we want to store is int, and the second is the next part. Now what will be the data type of next? Next is a pointer to the next node. It's a pointer to the next node. So the type would be node star next. Okay, and let's also create a constructor here. So if I'm passing any value v inside my constructor, so this will just create a new node for me, and it will put v as the value, and it will say next is equal to null. Alright, so this is our implementation of a node, of a single node in our linked list. Okay, how will we create this? For example, if I want to create a new node, I can say node star, my name of the node, is equal to new node and the value that I want to store in this node. Alright, and for example, I want to add another node in my linked list. So I can say new node 2, and I've stored 2 value in this new node, and I can make node 1 point to node 2. How? I can say node 1 next is equal to node 2. Next of node 1 is equal to node 2. So now these two nodes are connected to each other. So moving forward, let's see how do we traverse. Now I've created a linked list here in code, but how can I traverse my linked list? So I told you all I need to traverse my entire linked list is the head of the linked list, is the starting point of my linked list. So just try to imagine here, this is my linked list and the last node is pointing to null. Okay, and I have the head pointer which points to the first node in my linked list. So to traverse all of the nodes, what I can do is I can take a temp pointer which is at head, and I can keep moving temp by one step. How do I move the temp pointer to the next node? I can say temp is equal to next of temp. So this will move my temp pointer to here because this is the current temp next of temp. And similarly, if I keep repeating this, I will be able to traverse my linked list, right? Now, how will I stop? When will I stop moving my temp pointer one step forward? I stop when my temp is at null. So whenever my temp pointer reaches null, that means my linked list has ended and I can stop traversing it now. Alright, let's see it here. We'll create a function traverse where we'll be passing the head of my linked list. To traverse the linked list, we'll create a temp pointer which will start from head, and while temp pointer is not equal to null, while my temp pointer is not equal to null, I'll keep moving temp is equal to next of temp, and I'll also, before that, I'll also print the current element. Okay, to print the current element, I'll just print temp value. Let me put an arrow here so you'll be able to visualize better. So till the time temp becomes null, we'll keep moving our temp pointer forward and we'll keep printing the values. Alright, so let's create a head pointer here. Okay, we can pass the node 1 also because that's where our head will be, or I can just create another pointer node star head and make it point to my node 1, which is the first node. Alright, so I'll say here traverse and I'll pass the head of my linked list. So here what I'm getting is a linked list, okay, where the first node has value 1, the second node has value 2, and this pointing to null shows that this is where my linked list is ending. Alright, so this is how I can traverse a linked list. Now let's move forward to seeing how insertion happens in a linked list. And for insertion, we'll be seeing 3 scenarios, okay. First scenario is when we want to add a node at the start of my linked list. So for example, I have a linked list here. I have the head of my linked list and I want to insert a new node. Okay, this is my new node. So step 1 obviously will be to create my new node, and to add it to the linked list, what I'll have to do is the new node should point to the current head. Alright, so I'll say the next of new node should point to my current head, and once I have done that, I'll move my head pointer to my new node, and now I have added an element at the start of my linked list, right? And also, what will be the time complexity of this operation? The time complexity will come out to be O of 1, right? Because we're not traversing the list, we're not moving the elements, we're not doing anything, it's a O of 1 operation, right? We're just changing the links of the node. Alright, so it's an O of 1 operation. Let's see this in code. So void insert at head, and here let's say that we are being given the head and the value that we want to insert, the value of the new node that we want to insert and in our linked list. Now here, when we are passing the head of our linked list, we'll be passing it by reference and by not value. So I hope you understand the concept of pass by value and pass by reference. When we are passing by reference, we are actually sharing the address of our argument here. That means when we make inside this function, when we make changes to our linked list, those will be actually reflected here. If we just pass the head by value, not by reference, then whatever changes we do inside this function will only be seen inside this function. All right, so since we are just returning void here, what we'll do is we'll insert the element in my linked list, and for that operation to show here as well in my main function, I'll pass this by reference. Alright, so I don't have to return anything. Let's do this. First of all, create the new node. Alright, create the new node. So node star, let's call it new node, is equal to new node and the value that I want to insert in my new node. Alright, and now new node next, I'll make it point to my head pointer. Alright, whatever is the current head of my linked list. So I'm adding my new node in the beginning, and then I'll change the head pointer to point it to the new node. So now my linked list is starting from the new node. Alright, let's check this. I'll call this function insert at head, where I'm passing the head of my linked list, and I'll pass the value that I want to insert at the head, which is 3. And we'll call the traverse function again here, so that we'll be able to see the changes made in the linked list. So in the traverse function, why are we not passing by reference? Why are we passing by value? Because we're not making any changes to the linked list and we're just traversing the linked list in the traverse function, right? So we don't need to pass it by reference there. All right, let's run this. Did we have some syntax error? There's no syntax error, I think just something got selected by mistake. Okay, so we're able to see here this was our linked list before and I added 3 at the head of my linked list, all right? And even will this function work even if my linked list is empty? So if my linked list is empty, basically the head will be pointing to null. So in that case again, new node next will be null and head will come at new node. So in that case, I'll just be able to add one element, the first element in my linked list. Okay, so when writing these operations, just make sure of the edge cases. You know, what if my linked list is empty? Will I be, you know, still able to do this operation or not? Okay, so moving on, we'll be seeing how to insert an element at the end of my linked list. Again, let's try to imagine here we have a linked list with 3 nodes, right? And the last node is pointing to null and we have the head pointer. So if you want to add a node at the end, all right, that means here, first of all, we'll create this new node. Okay, we created this new node. Now to add this node at the end, we should be able to change this this link. We want this last node, the current last node, to point to the new node. And that's how I'll be able to add this at the end. So to do that, first of all, I'll need to get access to this last node. What is the current last node of my linked list, so that I can add the new node after it. So to get access to this, so this will become easier when we have the tail pointer. So in some cases, just how we are given head pointer, we are also given tail pointer. Tail points to the last node. But in this case, let's take it easy. Let's just have the head pointer. So if I want to get to the last node, I can just traverse, right? And we already know how to do that. I'll create a temp pointer and I'll keep moving the temp pointer until my temp pointer next is pointing to null. All right. So until my temp pointer next is not equal to null, I'll keep moving it forward. So when will it become null? When it is at my last node. When it is at my last node, then my work is easy. I'll just change this link. I'll make the next pointer of temp, which is my last node, point to the new node, and the new node will point to null. All right, and this is how I'll be able to insert at the end. And what will be the time complexity of this? The time complexity here would be O of n. Why? Because I'll need to traverse the entire linked list to get to the end node. If I'm already given the tail pointer, however, if I'm given the last node of my linked list, then it's a O of 1 operation. But if we are only given the head pointer, which in most cases will be only given the head pointer, in that case we would be required to traverse to the last node. So making it a O of n operation. Let's write the code for it. Void insert at end, and here again we'll be passing the head of my linked list by reference, and we'll passing the value of the new node that we want. So first of all, let's create our new node. So we created our new node, and now we need to traverse to the last node. You need to find the last node of my linked list. So for that, let's create a temp pointer starting from head, and while the next of temp is not equal to null, I'll keep moving my temp pointer one step forward. So at the end of my while loop, at this point, Now temp is pointing to, at this point temp will be pointing to last node. Alright, so at the end, for the next of the last node, I'll add the new node. Alright, and I don't need to do anything else because the next of new node will already be pointing to null, right? Because that's what we have added in our constructor over here. We added a new node at the end after my current last node. Okay, now here if I'm given an empty linked list, alright, if I'm given an empty linked list, meaning my head is null, at that point when the temp will also point to null, right? And then when I try to access next of temp, it will throw an error, right? So before this, let's check, okay, let's add a check for the edge case. If head is equal to null, meaning the linked list is empty, so we can just call the above function, which is insert at head. Okay, so if our linked list is empty, we'll let this function insert at head handle that. Alright, because if the linked list is empty, we won't be able to find the last node, which is what we need in this logic. We need to find the last node, but there is no last node if the linked list is empty. So, okay, common sense. Let's try this. Insert at end, and let's insert 4 and call the traverse function again here. Running this. And you see, this was my linked list after inserting 3 in the start, and this is my linked list after inserting 4 at the end. Alright, and finally, now let's see what I'll do to insert a node in the middle of my linked list. So we saw start and end, but also what if I need to add an element at some position that is given to me in the middle of my linked list. So for example, if this is my linked list, all right, and I'm being told to add a node at position 3, all right, so this is my position 3, so this is where I need to add my new node at position 3. Now to add my node here, let me draw it in the middle, okay, so easier to imagine. This is position 1, 2, and I want to make this as 3, alright. So for that, let's also draw the head pointer. For that, what I'll need to do is I'll need to change this link, right? So I'll need to change this link to point to this new node, and the new node should be pointing to this node after the position in which I'm inserting. Alright, so basically first of all I need access to this node, alright, so that I can change the next of this node, and this will be present at position -1. Okay, so if I want to add an element at some position k that is given to me, okay, let's call it k. If I need to add an element at position k, so first of all I need to access the node that is at position k -1, so that I can change its next pointer to point to the new node. Alright, and before I change that, I also need access to this node, which will be the node, if this is the temp node, or let's call it the previous node. So this is the previous next node. So before I change this link, if I change this link, I won't have access to the rest of my linked list, right? Because this is the only link that gets me to the previous, to this particular node. So before changing this node, what we'll actually do first is, we'll say the new node next, put it as previous next. let's understand again. What am I calling previous? First of all, understand that. Previous is the node, previous node is the node that is at position k minus 1. Alright. After which I need to add my new node. Now, previous of next will be the node that will come after my new node. So, new node next of new node should point to this particular node. So, once I have added that link, then I can change this link and make it point to the new node. So, I'll first do this. I'll say next of new node, make it point to the previous next, and then I'll say previous next, make it point to the new node, and that's how I'll be able to insert an element in the middle of my linked list at some position k. What will be the time complexity? The time complexity here in worst case would be O of n. Alright, if position is the position at which I want to insert is the last position, then I would be required to traverse the entire linked list. That will make the time complexity O of n, or in average case it will be O of k. Let's see the implementation now. Void insert at middle. Here, first of all, let's take the head, we'll take the value of the new node, and also we'll take the position at which we want to insert the new node. Okay. First of all, we need to find the node that is at position k minus 1. Alright, and to find that node, let's create a temp pointer. Let's call it previous. Let's call this previous pointer because I want this to point to the node that will be coming before the new node. And let's also create a count variable, int count is equal to 1. Now, while count is less than position minus 1, I'll move the previous pointer to point to next, and I'll do count plus plus. So now my previous pointer is pointing to the node before, to the node that should come before new node. Okay, and let's also create the new node first of all. Node star new node is equal to new node with the given value. And now here I'll say new node next of my new node should point to next of previous, and now previous next should point to my new node. Okay, I hope this is clear that first of all I'm changing the link where my where the new node should point to the node that should come after it, and then I'm making the change for the previous node. And this code right here will help us insert an element in the middle, but in this what approach we are going for? We are first of all finding the element that will come before that position, okay, before my new node. Now what if I pass the position as 1? If I pass the position as 1, that means I want to insert an element at the first position, that means at head. Alright, and for that this logic will not work because here we are trying to find the element that is before that position, and there is no element before position 1. Alright, so let's add the check for that edge case as well. If position is equal to 1, if you are trying to add an element or node at the first position, then I can just call my insert at head function. I'll say insert at head and the value, and I'll say return. Alright, so in that case I don't have to go through the entire flow. Here as well we forgot to add the return statement. So here in insert at end, if the head is null, if our linked list is empty, After calling this function, we'll say return, all right, so that the rest of the code does not get executed, or just add an else case, okay, whatever works. Just add a return statement or else for this if statement. Okay, so let's try to call this function now. Insert at middle, let's say head 5, and I want to insert at position 3. And we'll call the traverse function again. So this was my linked list, and I inserted an element, a node at position 3 with value 5. Okay, I can also check for other position if I want to insert at position 2. So I'll be able to insert here. If I want to insert at position 1, then that will call just the insert at head and insert it at the beginning. All right. So this is how insertion in linked list works. Let's move forward to the next operation, which is deletion. And again, here we'll be seeing deletion at start, at end, and in the middle. Okay. So how do we delete an element from the start? If you're given a linked list, okay, and I'm given the head pointer. So this is should be pretty easy, right? We just have to delete the node that is present at head pointer. But also we'll have to shift the head pointer to the next node, right? If I just delete this head node, how will I know where my linked list is starting? Where will the head pointer go, right? So before deleting it, I'll first create a temp pointer, okay, which will be pointing to the node that needs to be deleted, and then I'll move the head pointer to its next node, all right, to the second node, and then I can say that you can free temp. Okay, we'll be using a function free that will free up the space that is occupied by this temp pointer node. Again, the time complexity here would be O of 1, right? We don't need to traverse the linked list here. Void delete at start. We'll be passing the head. So first of all, let's say node star temp is equal to head. Head, I'll move it to the next node, the second node, which will become my new head, and then I can say free temp. Also, if my linked list is already empty, then there is no, node, the first node, the second node. So I can just say if head is equal to null, that means my linked list is empty. I can return. I don't have to do anything if my linked list is already empty. Okay. Delete at start, or let's keep this uniform. Let's call this delete at head. All right, and I'll pass the head here and call my traverse function. So 3 got deleted here from the start of my linked list. Okay. Deleting a node from the end. Again here, to delete the element from the end, the last node basically, I'll need access to the second last node, this node. Okay, this is my second last node. So using a temp pointer, I'll keep traversing my linked list until I find the second last node. How will I find the second last node? When my temp pointer's next becomes null. That means I've reached to the second last node. Okay, when my temp next. So if this is temp, the next and next. If that becomes null, then that means I've reached the second last node. when I have reached the second last node, I can make the last node, second last node, I can say, I can create a new pointer, you know, temp or just last node that will be pointing to my last node that needs to be deleted. And then I can change this link. I'll say the next of second last node should be pointing to null, and in the end I can free my last node. Alright, and the time complexity here would be O of n, because I'll need to traverse my entire linked list to reach to the end of my linked list. So let's write this function void delete at end, passing the head here. And what we'll do is first of all find the second last node. So to find the second last node, let's create a pointer temp, or let's call it second last node. Okay, so we know what we are going for. So I'm creating this pointer that is starting from head, and I'll say while second last node next is not equal to null. Till then, that time, move second last node one step forward. So this loop, when this loop ends, the second last node pointer will be pointing to my second last node. And what will be my last node? Node star last node. This will be equal to second last node nodes next. So next of second last node would be my last node. And then I can just say make the next of second last node point to null, and in the end free my last node. And for edge case, I can add an if statement here. If my head is equal to null, in that case my linked list is empty, so I'll just say return. And if my head of next is equal to null, that means I only have one element in my linked list. In that case also this logic will not work, because here we're trying to find the second last node. If there is only one node in my linked list, then there's no second last node, there's just a last node. Alright, so in that case I can just take help of delete at head function. Okay, if I am trying to delete one node that is present in my linked list, the last one node, then I can just call delete at head here. It will do the work for me, and I'll call return. Alright, so this will handle my edge cases if there is no node or only single node in my linked list. So let's call this function delete at end head traverse head. So here my last node was 4, and after deleting, this is the linked list that we have. Alright. Next part is deleting a node from the middle. So again here when we are trying to delete from the middle, we'll be given some position k from which we need to delete. Alright. So for example, we are given k is equal to 3. So that means this is the node that I need to delete. So to delete this node, I first need access to the node that is before it. Right? I need access to the node that is before it. So I'll use a pointer, previous let's call it, to make it point to the node that will be at position k minus 1. So I'll reach the position k minus 1 just like I reached while inserting an element. I'll reach the position k minus 1 and get the previous node. Now the previous node's next is the node that I want to delete. Okay, so let's call this current node that I want to delete. And then I'll point where should the next of previous point? I'll have to change this link, right? So I'll make this point to this node. How? I'll say the next of previous should be pointing to my next of current, which is this. Okay, if this is current, then this is next of current. So this is how I'll be able to connect previous with the next of current, and then once I've done that, then I can delete this current node. Okay, and the time complexity here would be O of n in worst case, alright, in case I have to, if n is equal to k, I have to traverse the entire list. So void delete at middle, where we'll be given the head of my linked list and the position at which I want to delete element. Okay, so first of all, let's create a pointer for traversing. Let's call it previous and make it point to head, and also create another variable count so that I can count till k minus 1 position if the position given to me here is k. Okay, so while count is less than position minus 1, till then keep moving previous to next node, and I'll do count plus plus. So now previous is pointing to the node at position k minus 1. Okay, previous is pointing to node at position minus 1. Okay, if position is the value that is given to us. So the current node, the node that needs to be deleted, let's call it current node will be next of previous. This is the node to be deleted, and I'll say before deleting it, I'll say the next of previous should be pointing to the next of current. Okay, so the node that needs to be deleted, I'll connect the previous node of it and the next node of it, and then I will free my current node. Alright, again here to take care of the edge cases, we can just see, we can check if position is equal to 1. Then this will not work because we're trying to find the node that is at position minus at the position before the position that needs to be deleted, right? So that won't work when we are trying to delete the node at position 1. So in that case, I'll just call the function delete at head. Delete at head. So calling this function delete at middle, did we add a return statement? We'll also add a return statement here, so the rest of the code does not get executed in the function. So we'll say head at position 2 and then traverse head. So this was our linked list, and the element at position 2 was 5. So 5 got deleted from my linked list. Okay, if I try to delete the element at position 3, in that case 2 will get deleted, and if I try to delete at position 1, in that case 1 got deleted. Alright, so this was insertion and deletion. One last thing is updation of a node. If I want to update a node at a particular kth position, so again you should be able to do this pretty easily. If I have a linked list and I have some position k and I want to update the value at that position k, okay, for example k is equal to 3 and I want to update the value at this position, so I can just use a temp pointer that will be starting at my head, and I'll keep moving it till I reach k position, and at that position I can update the value. So this should be easy, right? Let's just implement this quickly. Update node value. So I'm given the head and I'm given the updated value. let's call it updated value, and I'm also given the position at which I want to update. Okay, so let's call it K. So I'm given three things: the head of my linked list, the K position at which I want to update, and the updated value. So first of all, we'll create a pointer temp, make it point to head, and let's also create a counter which is equal to 1. Now while count is less than K, we'll keep moving our temp pointer by one step, and we'll keep doing count plus plus. So now after this loop ends, that will end when our count becomes equal to K. At that point, our temp will be pointing to the node at kth position, and now I can just update its value. I can say temp value, make it change to the updated value. Alright, so right now what is the linked list that we have in the end? This is the linked list that we have. If I want to update node value in this linked list at position 1 with value 8, let's see if our function works. So now you can see here at the position 1, I updated the value from 5 to 8. Okay, you can also update it at position 2, from 2 to 8. Alright, so this is how we insert elements, delete elements, update elements in my linked list. And also, what is the time complexity for updation? It will be O of K, and in the worst case this will be O of N, right, in the case that K is equal to N. Now let's test whatever we've learned so far in linked list and try to solve some questions, starting with very easy level questions, and then in the coming videos we'll move forward to medium level questions, and we'll cover some hard level questions as well. So the first question is, given the head of a linked list, we have to delete every alternate element from the list starting from the second element. Alright, so if this is our input, the output looks like this, where we're deleting the every alternate element starting from the second element. Alright, so let's try to see how we can implement this in code. Let's start with 4 elements. If we're given 4 elements, okay, and we need to delete every alternate element starting from second element, meaning we need to delete this one and this one. Okay, and obviously the head of the linked list will be given to us. So we need to delete the element that is after the head, right? So first of all, let's take a temporary pointer, okay, through which we'll be traversing our linked list. And if we start our temporary pointer from head, we need to delete the node that is after my temporary pointer. So where would the next of temporary go? If we delete this element, where would this link go? This will go to the element after the node that we are deleting. Alright, so what we'll do is we'll call this element as delete node. Okay, this is the node that we need to delete. Okay, let's call it delete node. So delete node will be the next of the temp node, and the next of temp, meaning this link, will remove, and we'll make temp next point to temp next next. That means this node right here. So now temp next is pointing to the node that is after the deleted node. Alright, and then now since I have changed this link, I can conveniently delete this. Now I have to repeat the same thing till I have deleted all of the alternate nodes. So I'll just move the temp to temp of next. So I'll move my temp pointer to its next, which will be here. And I'll go through the same process again. I'll say, okay, this is the node that needs to be deleted. This we've already deleted. And we'll change this link. We'll change this link and make it point to null. So temp of next will point to temp of next, which will be null here. And then we'll delete the delete node and we'll move the temp to temp of next. So we'll keep doing this till the temp reaches null. Now the temp will reach null in case of even elements. What if we have odd elements here? Instead of null, we have another element here. So we have odd elements, odd number of nodes, and this is pointing to null. In this case, when I do temp is equal to temp of next, basically my temp pointer will come here, right? So again here there is no node after this that needs to be deleted. So in this case my stopping condition would be when temp of next becomes null. Okay, so when I have even number of nodes, my stopping condition would be when temp becomes null, and when I have odd number of nodes, then my stopping condition would be when temp of next becomes null. Alright, so we don't actually need to count if we have odd or even nodes. We just keep the stopping condition if any of this condition occurs first. If temp becomes null, we reach the null pointer while traversing through temp, or the temp of next of temp becomes null. In both of the cases, we'll stop traversing. Alright, and we'll return whatever the list is currently. So let's see this in code now. So we'll use the class node that we already created and the basic functions that we have seen to create a linked list. Let's first create node star head is equal to null, and then we can use insert at end function to just insert values into my linked list. So let me just copy paste this and change the values here. Perfect. Alright, so I have a linked list. You can call the traverse function to see what our linked list looks like, and we'll take this linked list as an input to get the output for deleting every alternate node. Okay, so let's write the function for that, delete alternate node, where we'll have the head of our linked list. So what do we do first? Let's first try to create our temp pointer, okay? That would be starting at head. And we basically need to keep moving this temp pointer forward till the entire linked list is covered and we have only the alternate elements left. So in the while condition, we'll say until temp is not equal to null, and so we're putting and condition here. So if any of these condition becomes true, we will just stop there. If temp becomes null or next of temp becomes null, in both these conditions we'll stop traversing. And next we find what is the node to be deleted. The delete node will be next of temp. Okay, this is the node that we need to delete. And before deleting it, let's first alter the links. So now temp of next should be pointing to next of temp should be pointing to next of temp. Okay, because we want to leave out the node in the middle, and we'll move the temp pointer to its next node. In the end, we can free up the delete node. Alright, and here we can already see that the while condition will be taken, the edge case will be taken care of. If the linked list is single, then this will never be called, right? And if the linked list has only one element, only one node, even then this loop will not run and nothing will happen, right? So we're good. So let's try this out. Delete alternate node. node where we'll pass the head node and then traverse and see what our linked list looks like. So this was our linked list, the one that we created, gave it as input, and this is our output, right, where 2 and 4 are the alternate elements that have been removed. What if we have odd number of elements? Let's see if our code still works for that. So I just added another node at the end, which is 5. So again here we can see 2 and 4 removed as the alternate elements. So our code works, and what will be the time complexity? The time complexity of this operation would be O of n, right? Because we're traversing our entire linked list. Moving on to the next question, which is finding the middle element of a given linked list. So given a linked list, we have to find what is the element that is right at the middle. Okay, so one way to do this is to find the length of my linked list. So for example, if I have this linked list, I can traverse the entire linked list like I do for printing, and I can count the length of the linked list. So here the length will come out to be 5. So if there are 5 elements in my linked list, so I know the middle element would be present at 5 by 2 plus 1, I can say. So that means that the middle element would be present at 3rd position, which is this. Firstly, we'll need to traverse the entire linked list to find the length of the linked list, which is easy. We know how to traverse the linked list. We just need to keep a pointer and keep increasing it to find the length. And then we need to traverse the linked list again till the middle element to return the value of the middle element. In this solution, we'll be traversing our linked list twice. Okay, first we'll be traversing the entire linked list, and then we'll be traversing half of the linked list. This is of course a valid solution that we've just discussed, but there is another slightly more optimized solution to this question as well, and for that we follow the approach of slow and fast pointer. Slow and fast pointer. So try to understand, for example, we have a racetrack over here, okay, and there's one person called slow, another person called fast, okay. Now the slow person moves with the speed of x, let's say, and the fast person moves with the speed of 2x. So basically fast person is moving with the speed double of the slow person. So in the same time, if fast is covering this entire distance, d, let's call it, the slow person will cover only half of the distance. Does that make sense? Because fast is moving with the speed of, is moving at double the speed, then that means in the same time, fast will be able to cover double the distance because fast is moving at double the speed. Okay, so with that approach, we can use that to find the middle element, because when we can say that the fast, in the time that fast will cover the entire distance, that means in the time that the fast will cover the entire linked list, the slow will cover only half of the linked list. And so I can say when fast reaches at the end, slow will be at the middle. When fast reaches at the end, slow will be in the middle. So now how to imagine this in a linked list? Of course, there are no persons running in a linked list and there's no speed, but we'll be talking about pointers here. So try to imagine we have a list here, okay, and this is our head. What we do is we take 2 pointers. One is slow and one is fast. Now I am saying fast is moving at double the speed. That means if slow is moving by 1 node, then fast will move by 2 nodes. If slow pointer is moving by 1 node, fast will move ahead by 2 nodes. So in the first chance, slow reaches here and fast reaches here. In the next chance, slow will reach here and fast will reach here. So fast is moving by 2 steps. Now here, fast has reached the end of my linked list, and so slow will be at the middle of my linked list. So if you see this, this is for even elements. So in even elements, when my fast pointer reaches null, then that means my slow pointer would be at the middle element. And if we have odd number of elements here, okay, if we have another element here and this is pointing to null. So when fast reaches here on my last node, again my slow would be at the middle element. So I can say the fast element, when it reaches null or it reaches the last node, at that point my slow pointer would be at the middle node. Okay, so common sense, like really the intuition behind this solution is just that if something or someone is moving at double the speed, then at the same time they'll be able to cover double the distance. Or another way to say it, if something or someone is covering has a speed of half, has half of the speed, then they'll be covering half of the distance in the same time. So slow is covering half of the distance in the same time that fast is covering, okay, the full distance. So slow will be at the middle element when fast reaches the end of my linked list. Okay, so let's see this in code now. Void find middle node, where I'm passing the head of my linked list. Okay, so we already have a linked list created here. Just need to write the function for finding the middle node. So we'll create 2 pointers, slow and fast, both will be at head in the beginning. And we'll say while fast is not equal to null and fast next is not equal to null. Till that time we'll keep moving forward. This basically means that till the fast pointer doesn't reach to the end of my linked list. Okay, so if there are even a number of elements, then the loop will be terminated by this condition. If there are odd number of elements, then the loop will be terminated by this condition. So till this happens, I'll keep moving the slow and fast pointers in the way that slow will be moving by 1 node and fast will be moving by 2 nodes. Okay, so slow is equal to next of slow and fast is equal to next of fast. All right, and when the fast pointer reaches the last element or null, at that time slow will be at the middle element. Slow is now at the middle node, so I can just return, let's change this to int, and I can return the middle node value. So slow value I can return from here. Okay, and here let's try to print find middle node in my linked list. Running this, so this is returning 3 to us in my linked list. Okay, and if I add another element here, then again here also 3 would be my middle node. So in today's lecture, we were able to see what is linked list. We saw the basic operations, insertion, deletion, traversal, updation, and we solved a couple of easy level problems. In the next video, we'll be looking at some medium level problems on linked list. In today's lecture, we'll be looking at some medium level problems on linked list. So I hope you have covered the last lecture where I discussed what exactly is linked list and some of the basic operations on linked list. that would be important to cover that, to understand that completely, so that we can start and solve some medium level problems. All right, starting with the first one. The first problem is given two linked lists, tell if they are equal or not. And when are two linked lists equal? They're equal if they have the same data and the arrangement of data is also the same. So for example, we have this input where we are given two linked lists. The output here should be 1. It's a typo, but we can see that these linked lists are they have the same data and also the same arrangement of data, so we can say that these two linked lists are equal. All right, now how do we check that? We can check that using two pointers. So we can create two pointers. One pointer would be here for list 1 and another pointer for list 2. All right, let us see like this. So I have one pointer here and I have one pointer here. Okay, let's call it head 1 and head 2, and we can just keep comparing the values of head 1 and head 2 of these two pointers. If at any point they become not equal, then that means that my two linked lists are not equal and I can return false. If not, I can just like keep moving forward. I'll check for the next elements and compare those. Okay, and till when will I keep doing this? Until one of the or both of the heads become null. So at some point both of these pointers will reach null. Now it is important that both the pointers head 1 and head 2 reach null at the same time. For example, if head 1 reaches null but head 2 does not reach null, for example, here we have another element 6 after 5. At this point, of course, we cannot compare null and 6. So we'll just break the loop and we'll see that head 1 and head 2 are they both equal to null. Okay, so we'll keep checking, we'll keep traversing the two linked list until one of the pointer becomes null, and in the end we'll also check that both of the pointers should be pointing to the null at the end and not just one. Okay, so let's look at the implementation here. Let's create a function that returns a boolean value, bool check equal, and here we can expect two linked lists, basically two heads, and we don't need to pass the head values by reference because we're not actually making any changes to the linked list. We're just checking to see if they're equal or not. Okay, and that's why we can just use their head pointers to traverse the both of the linked lists. So we can keep the condition for the while loop till head 1 and head 2 do not become equal to null. Okay, this means that both of these are not equal to null. Till that time, we'll keep checking if head 1 value is equal to head 2 value, or let's say if head 1 value is not equal to head 2 value. If they become unequal at any point, then I can simply return false, because that means these linked lists are not equal. Or else if they are equal, then I just need to move my pointers forward. So I'll say head 1 is equal to head 1's next, and head 2 is equal to head 2's next. Okay, so at the end again we need to check that both of these pointers become null at the same time. So while returning, we can either add it as a condition, or we can just return the result of head 1 is equal to null and head 2 equal to null. Okay, so if one of these, not and, we should say or, because we want both of these values to be null. Okay, so if only one of the values is null out of head 1 and head 2, then these linked lists are not equal. If both of the values head 1, head 2 not values, I should say the pointer values are null, then that means that these two linked lists are ending at the same point and they are in fact equal. Okay, so let's create two linked lists here. So here we'll return, we can either add a if condition or we can just return the result of head1 equal to null and head2 equal to null. So basically we want both of these pointer values to become null at the same time, and this will return true only if both head1 and head2 become null. Alright, so let's create our two linked lists here. And I'll just print the result of check equal, where I'll pass head1 and head2. So right now these two linked lists are equal, so it should return 1, but if I remove the last node of my second linked list, it will return me 0. And the time complexity of this solution would be O of n, where n will be the length of the linked list that is shorter. Our next question would be reversing a linked list. So if this is the linked list that is given to us, we have to reverse it. Not just print the reversed list, but actually reverse the links of my list. That means the list that should come out to be should look like this. This is the reverse link, where you'll see now 5 is pointing to 4, 4 is pointing to 3, 3 is pointing to 2, and 2 is pointing to 1. So you're understanding, we're not just printing the values or the list, or we're not just traversing the list in a reversed manner, but we're actually reversing the links of my list here. So how can we do that? Let's try to understand. Let's take a few elements, 1, 2, 3. Okay, let's take, we have these 3 elements in my linked list. Now if I am to reverse the list, that means I have to reverse the link. I have to reverse these 2 links, so that 2 points to 1 and 3 points to 2, and also 1 should point to null, right? So basically 3 links for these 3 nodes I have to reverse. So if we do this 2 at a time, for example, I say let's first take just these 2 elements, okay, and reverse this. I can do that by taking 2 pointers. For example, I take a pointer to 2, which is current, and 1, let's call this previous, okay. And I say, now what you do is you put current next as previous. So what will happen is this link will get removed, okay, and we'll have another link where 2 will be pointing to 1 instead of 3. Now if we do that, we have lost here the access to the rest of my linked list, right? How do I access the rest of my linked list? That is after 2, because now I have already changed the next of 2, so I don't have access to what was there previously. So I'll actually have to make use of 3 pointers here, okay. If I can have another pointer before changing this link, if I create another pointer, and let's just call it the next pointer, and make it point to 3. In that case, even if I remove this link and reverse it, make it point to previous, I still have access to 3 through the next pointer. Okay, so we basically will need to have 3 pointers here. Okay, previous and current between the previous and current nodes will be reversing the link, and we'll be using next to see what will be our next set of previous and current nodes that we'll need to reverse. Okay, if you don't exactly understand yet what we're doing here, it's fine. Let's try to see with a proper example. But what I was trying to explain so far is that we'll need to keep track of the nodes with the help of 3 pointers. Okay, so let's take another example. Let's have 4 nodes here. Okay, so this is my linked list, and what I'll do here is I'll start with 3 pointers: previous, current, and next. Okay, and let me start with my current pointer here on the head. Okay, this is my current head of my original linked list, and I'll make previous point to null, because you see, after I have reversed, okay, in the reversed linked list, the first node, the original head node, would become the last node of my linked list, and the last node of my linked list always points to null. Okay, so I have to make one point to null. So what we'll do is we'll start with the current pointer at head, we'll make another pointer previous that will be pointing to null, and we'll say, okay, next pointer will be the next of current node. Okay, so now what we do is we say reverse the link for the current node. So this link will change, and instead we'll have this link. So in current next we'll put previous. Okay, once we've done this, we'll just move all of these 3 pointers, previous, current, and next, by one step ahead. So that means the previous pointer will come here where current was, the current pointer will come here where next was, and the next pointer will always be next of current. Okay, and then we just keep repeating the same thing. So in current next, we change the link to make it point to previous node, and then we shift all of our pointers. So if we shift, we'll have previous here now, current where our next was, and next will be next of current. Okay, once again we'll change the next link for current node to make it point to previous node, and we'll shift all of our pointers by one step. So now previous is here, current is here, and next is here. Once again we'll change the link of current node to make it point to previous, and we'll shift our pointers. So now previous is here on my last node, okay, and current is here. Now I don't need to move any further ahead in my linked list. I have reversed my entire linked list. So I can say whenever my current pointer reaches null, then that means the entire linked list has been reversed. And what will be the new head here in my reverse linked list? The new head will be at previous. So this will give me my new head of the reversed linked list. Okay, so when current reaches null, that means my entire list is reversed, and at that time previous pointer will be pointing to the new head of my linked list. So let's see this in code now. We'll create a function reverse linked list where we'll be passing the head of the original linked list. The first step would be to create the 3 pointers. So we have 3 pointers, previous, that would be pointing to null. We have another pointer, current, that will be at head, and we have next pointer. Okay, so next pointer we can make it point when inside our loop. So we'll create a loop, and this loop will run till our current pointer reaches null. Okay, so till the current pointer is not null, we'll keep running this loop, where we'll first of all say make the next pointer point to next of current node. And once we've done that, now we can change the link of current next and make it point to the previous node. And now what we have to do is just move our nodes ahead. So we'll make the previous point to where current was, and we'll make current point to where our next pointer was. Okay, so this loop will keep running until current reaches null at the end of the linked list, and when it does, then previous would be pointing to the new head. So we can say our new head will be at the previous pointer, and that's all that will take us to reverse the linked list. We can either return the head of the reverse linked list, or because we're just passing here by reference, I can just change the head and point it to my new head. Okay, so we've created a linked list here, and let us call the reverse function here, passing the head, and then traverse my linked list. Okay, so let's run this, and you can see this is my original linked list, and this is right here my reversed linked list. Okay, so that is how you can reverse a singly linked list. Moving forward to the next question. Let's see, what does the next question tell us to do? The next question says, given the head of a linked list, determine if the linked list is a palindrome or not. Now, firstly, let's understand what exactly is palindrome. So, a palindrome is a sequence that reads the same if you read it from forward or backward. So, for example, if you take this linked list, if you traverse it from the forward or you traverse it backwards, it will be the same. Similarly, if I have another linked list, this will also be a palindrome, because in any direction you try to traverse the linked list, it will be the same, right? So how do I now check if a particular linked list is palindrome or not? Now, one way to do it is reversing the linked list. So what I can do is create a copy of this linked list that is reversed. Okay, so I can reverse the entire linked list, and then if I reverse this linked list, I'll get the same one, right? And can I say if I compare these and these come out to be equal, then I can say that this linked list is palindrome, right? Similarly, if we take a non-palindrome linked list, okay, suppose I take this linked list. If I reverse this, the reverse linked list will come out to be something like this, and these linked list 1 and 2 are not equal, so I can say that this linked list is not a palindrome, right? So that is one way to do it, to reverse completely and then check equal. So basically just doing what we have done in the last two questions. Okay, we first reverse it and then check if it's equal or not. So that is one way to do it. Another way, a slightly better way to do it. So in this solution that we just discussed, we'll have to reverse the entire linked list and check if both are equal, right? So reversing the entire linked list will take O of n time, and then checking if they're equal or not will again take O of n. So another thing that we could do is if we can find the middle point of our linked list, which we have seen in the last lecture how to do that. If you can find the middle point of my linked list and then divide the linked list from there, not divide it actually, but just after the middle point, if I can just reverse half of the linked list, the second half of the linked list. So don't reverse the entire linked list, but just the second half, and then compare it with the first half. Okay, so what I'm saying is, if suppose this is my linked list, so what we do is first of all find out the middle node. Okay, so 4 is the middle node. So starting from the middle node, just reverse the second part. If I reverse this part, what will this part of the linked list look like? It will look like something like this. This is the reverse part. All right, and then I compare the first half and the second part. So what I'll do is, my first half is this and my second half is this. Okay, and are they equal? They are equal. Then that means that this is a palindrome. All right, so basically I'm saying we don't have to check the complete linked list, we don't have to compare the complete linked list, we just have to compare the first half of it and the second half of it, which would be reversed. Okay, so this is something that we can do, right? Because we've already seen how to find the middle point, we've already seen how to reverse the linked list, and we've already seen how to compare if they are equal. All right, so this should be pretty easy. Let's just go through the solution again that we'll be following. Okay, so if this is our linked list, what we'll do is first of all find the middle node. And how will we find the middle node? Using slow and fast pointer. Okay, and this approach basically says that the fast pointer will be moving it by 2 nodes, slow pointer will be moving by 1 node. So when the fast pointer reaches the last node or it reaches null, at that time our slow pointer will be at the middle node. If we have our slow and fast pointers here, in the next iteration of the loop, we'll have the slow pointer here and fast pointer here. In the next iteration, we'll have the slow pointer here and fast pointer here, okay, on null. So now when our fast pointer has reached null, I can say that the slow pointer is pointing to my middle node. So found the middle node. What I'll do then is, starting from the middle node, I'll reverse the rest of the linked list. Okay, so this I'll call it current node. I'll make previous pointer point to null and the next node point to next, just like we did while reversing. All right, so we'll say change the link of current to make it point to previous. So 3 will point to null, and then we'll move all of the 3 pointers. So now previous is at 3, current is at 1, and next is at null. Okay, and now again we change the link of current node, make it point to the previous node, and then move all of the pointers. So now my current reaches null, and when my current reaches null, that's when I know that I've covered the linked list that I was supposed to reverse, and my previous will be pointing to my new head. Okay, so let's get rid of this now. We just need the new head. So we have one head that is here, that is the original head of my linked list, and another head, let's call it new head, or let's call it head 2. Okay, so head is the original head of my original linked list, and head 2 is the head of the reversed linked list of the second part of my linked list. Okay, so now what I have to do is, if you look at the head linked list, that is 1, 3, 3 and null, and head 2 linked list is 1, 3 null. So basically I'll compare these two linked lists till head 2 does not become equal to null, because the second part of my linked list will be the shorter one, right? So just as head 2 becomes null, I'll stop comparing. Until that, I'll just check if these two linked lists are equal or not. Okay, and when I start checking, I'll see, okay, 1 and 1, they're equal, 3 and 3, they're equal, and in the next chance head 2 will reach to null, and that's when I'll stop comparing and return true, because so far the linked lists were equal. Okay, so again the time complexity here would be O of n only, but slightly better, because here we won't have to compare the entire linked list, but just one half of it with the other half of it, right? So let's try to implement this now. We'll create a function that returns Boolean value, check palindrome, where we'll be getting the head of my linked list and just passing it by value will do. Also, let's add an edge case if head next is equal to null, meaning that my linked list has only one node. In that case, it will be considered a palindrome only, so I can just return true from here. The first step is to find the middle node, and for that let's take two nodes, slow and fast, both pointing to the head. While fast is not null and fast next is also not null, okay, because it can be either of these two conditions depending on we have even nodes or even number of nodes or odd number of nodes. So while fast pointer and fast next is not null, till that time we'll keep moving. We'll move the slow pointer by one step and we'll move the fast pointer by 2 steps. Okay, so now our slow pointer is at the middle node, and we'll move to step 2, which is reverse the second half of linked list. So my slow is at the middle node, so I'll make the current pointer point to where my slow pointer was, and I'll create another pointer previous where null was, and another pointer next. So while current is not null, I'll say first of all next is equal to current dot next, and now we can change the link of current dot next to point it to the previous node, and now shift the pointers. Previous will come where current was and current will come where next was. Okay, now at the end of this while loop, we'll have the second half of the linked list reversed, and we'll have the previous pointer pointing to my new head. All right, just like we saw in the last question. So third step is comparing the two halves, and so the first linked list, so the first part of the linked list I can traverse that using head pointer, and the second half of the linked list, for the second half of the linked list I can create another pointer head 2, which will be at current previous node. To compare, we'll start a loop till the time head 2 does not become null, because the second half of the linked list will be the smaller one. So while it does not become null, we'll keep checking. If head dot value is not equal to head 2 value. In that case, return false. That means our linked list, the two halves of the linked list are not equal. If not, then we'll just keep moving our pointers ahead. So I'll say head is equal to head next and head 2 is equal to head 2 next. And if I finish this entire loop without returning false, then that means that the two halves are equal and the list would be a palindrome. Okay, now let's check here with an example. So I've created a linked list here. Let's create a palindrome first and let's print the result of check palindrome function where we'll pass the head of my linked list. So this is my linked list and it returns 1, meaning it is in fact a linked list. What if I change it to not a linked list? So now it is returning 0. And let's also check with odd number of nodes. If I have odd number of nodes, this is still a palindrome, so it returns me 1. Alright. So this was the code for checking if a particular linked list is palindrome or not. Let's move forward to the next question, which is given a linked list, rotate the list to the right by k places. Okay, so what this means is we'll be given some value k. For example, here it is 2 and we have to rotate the entire linked list by 2 places. Okay, so if this is our linked list, if I rotate it once, what will happen is 5 will come at the beginning. Okay, so my linked list, if I rotate it once, it will become 5 will come at the beginning, then 1, 2, 3 and 4. If I rotate it again, then 4 will come at the beginning. So now my linked list will be 4, 5, 1, 2 and 3. Okay, and this will be the linked list when I rotate the list by 2 places. Okay, so this is my output. So you understand now what exactly we're being asked to do. Now, we don't have to rotate the list one by one. Okay, we can rotate by k directly by moving the last k nodes in front, right? So if I have this linked list, okay, and the k given to me is 3, then that means that the last 3 nodes, okay, will come in the front of my linked list. Basically this part, last k, these are last k nodes. The last k nodes will come in the front of my linked list. So if I move this to the front, that means 4, 5, 6. And then after 6, what will come? After 6, we'll start again from the head. So 1, 2 and 3. And after 3, I should have null. Okay. So we understand now what we are supposed to do. Let's move to the implementation part. How exactly will we do this? If we are given k is equal to 3, okay, first of all, to move these nodes at the beginning, okay, first of all I need to change some links here. Currently 6 is the last node and it is pointing to null, but after shifting by k, I know that these k nodes will come in the front. That means what will come in the next of 6 will come my current head. Okay, so number one step would be find the last node and make it point to head node. Okay, so for example, I find out that okay, 6 is my last node. So 6, I'll make it point to my head, which is 1. Okay, so now this is what is called a circular linked list. So now the last node is basically pointing to the head node, and there is no last node in my linked list. None of the nodes are actually pointing to null. So we don't know where this linked list is starting or where this linked list is ending. Okay, I mean, we know where it's starting at the head node, but that's not where it should start, right? So where should it be starting? It should be starting here at 4, and where it should be ending? It should be ending at 3. Now, how do I know? Let's first take care of the ending part. How do I know where it should end? If the length of my entire linked list is n, okay, if I have n nodes, and if I'm moving the last k nodes in the front, then my last node would come out to be the n minus kth node, right? Because the rest k nodes will come in the front. So n minus kth node, which is here 3, would become my last node in my rotated linked list. So another thing that we need to do is find n minus kth node and make it point to null. Okay, so now this 3 is pointing to null. Now the only thing that is remaining is the head. Where will the head go? The head will be here, the last kth node, the kth node from the end. Okay, so the kth node from the end, I can either check that, you know, I can either traverse the linked list in reverse, but that is a bit complicated, or else I can just say that this is the, if 3 is my n minus kth node, then 4 is my n minus k plus 1th node, right? N minus k plus 1th node. So before changing 3's pointer and making it point to null, before that I can make a pointer and say, okay, this is my new head. Okay, so what I'm saying is this will become, so what I'm saying is that this will become my third point. This is my third point, and the second, this will be my third step, and the second step would be find n minus k plus 1th node and make it new head. Now is my new linked list ready? If you see, the new head is here at 4. That means here is where, this is where my linked list will start at 4. So 4, 5, 6. After 6, I have 1, 2 and 3. 3 will be the last node. Okay, so if I write this properly, this is nothing but the same as this. Okay, so I have my output. So basically I have to do 3 things. First of all, I have to find the last node, okay, and make it point to head. Then I have to find the n minus k plus 1th node, and for this I'll also have to find n. Okay, so we'll have to find the number of nodes in my list. That I can do easily, just like we traverse our entire linked list. we can find, while traversing, we can make a pointer and just keep increasing our counter to get the total number of nodes in my linked list. And once I have the total number of nodes, that will be my n, then I can calculate n minus k plus 1th node where that will be residing and make it point to my new head. My new head is ready, and last step would be make the n minus kth node point to null, so that I know that's where my linked list ends. Okay, now a few things here. First of all, this we can combine when we are trying to traverse the entire linked list to find the last node. In the same step, we can find n, okay, because here for finding the last node also we'll have to traverse the entire linked list, and for finding the number of nodes, total number of nodes, we'll have to traverse the entire linked list. So both of these steps we can do in the same loop. Okay, and after that, if we can just find the n minus kth node, I know that the next of it would be n minus k plus 1th node. Okay, so I don't have to loop till n minus k again and again. Third thing, I'm trying to find n minus k here, but what if k is more than or equal to n? What if k is more than equal to n? So what if k is more than equal to n? So try to understand this, okay? If I have a linked list which looks like this, okay? Now, and my k value here is 4. Okay, let's just take 3 elements. My k value here is 4, which is more than n, which is the number of nodes. So what will happen is when I rotate it once, 3 will come in the beginning. Now for k is equal to 2, 2 will come in the beginning, and for k is equal to 3, again 1 will come in the beginning. So this and this is equal, it's the same linked list. So basically, if k is a multiple of n, then after rotating the linked list will look the same. If k is a multiple of n, after rotating it will look the same. And if not, if k is more than n, okay, so for k is equal to 4, what will happen? Again 3 will come in the beginning. So now this and this is equal. What we were getting at k is equal to 1 is the same that we are getting at k is equal to 4. So that means we can find out the actual value of k should be k modulo n. Okay, so for example, if here k is given to us 4, I can say k's real value, the real number of rotations that we'll have to do, that will be equal to 4 modulo 3, that is equal to 1. So 1 is the rotation that I need to do, and not the original k that was given to me, which was 4. Okay, so while solving, we'll take care of this. We'll find the actual number of rotations by using this formula, k is equal to k modulo n. Modulo here gives us the remainder when k is divided by n. Okay, and if k is equal to, after this, if k comes out to be 0, if the remainder comes out to be 0, then that means it requires no rotations. Okay, so that would be the solution of this question. Let's go forward to the implementation. So void rotate by k, and here we'll be getting the head of my linked list, and I'll get some value k. Okay, so first of all, let's check the value, get the actual value of k, the actual number of rotations that we'll have to do. That will be equal to k is equal to k modulo n. Okay, also we need to find n first, because that is something that is not given to us. Okay, so let's say node star temp is equal to head, and I'll make a variable int n is equal to 1. Now while temp next is not equal to null till I don't reach the last node basically. I'll keep increasing the value of n, and I'll also keep moving temp pointer to next. Okay, so now here we have the value of n, which will give us the total number of nodes, and also temp will be pointing to, temp is pointing to last node, right? Because when temp will come at the last node, that's when temp next will become equal to null and the loop will break. Okay, so now we have the value of n, so we can find k is equal to k modulo n, and if k comes out to be 0, then I can just say return, right? Because I don't need to do anything, then it will be the same list that I currently have. Okay, so if this does not happen, what we need to do, we already found the last node, so we make the last node point to head. Okay, so the first step, which is make last node point to head. So last node is currently being pointed to by the temp pointer, so temp next is equal to head. The second step, find n minus kth node. So for that we can create a loop. Okay, and let's create a pointer as well. We can use the temp, reuse the temp pointer actually, make it point to head, and then I can create a loop here for I is equal to 1, I is less than n minus k, I plus plus. I'll just keep moving temp pointer ahead. So at the end of this loop, now I have the temp pointer pointing to n minus kth node. Okay, temp is pointing to n minus kth node, n minus kth node, and my new head, where would that be? My new head will be at the n minus k plus 1th node. So basically my temp next will be my new head. This is the n minus k plus 1, this node. Okay, so I have my new head, and the third step was make n minus kth node point to null. So I can just say make temp next is equal to null. So second step was find n minus kth node and make next node as new head. Okay, so we did that here, and we made the n minus kth node point to null. Okay, at the end we can either return the new head of my rotated linked list, or I can just say head is equal to new head. Okay, so now the head pointer will be pointing to where the new head is, and let's test this. Rotate by k, where I'm passing my head and I'm passing k is equal to 2. So you can see here, this is my original linked list, and by rotating the list by 2 steps, this is my output. Okay, if I change k value to 3, then the last 3 numbers 3, 4, 5 will come at the beginning, right? So looks good, and you can see if I pass k value equal to n, nothing happens. If I pass k value more than n, 6, then only that is equal to passing k is equal to 1. This is how we rotate a linked list by k steps, and the time complexity of this would come out to be O of n. right? Because we're traversing the entire linked list to find the last node and also to find the number of nodes in my linked list. Let's move to the last question for this lecture. This question says we are given two sorted linked lists and we need to merge them into one single linked list such that the resulting list is also sorted. So sorted meaning all of the elements in my linked list, all of the values in my linked list, they are sorted in ascending order. So you can see in the list 1 that I have, all of these values are sorted 1, 3, 5, 6, and in the list 2 as well, these values are sorted 2, 4, 7. And now what I need to do is combine these two linked lists into a single linked list such that the combined linked list is also sorted. So my output should look like this. Okay. What comes to my mind is, one way to do this is, for example, if I have these two linked lists, okay, and I need to create a third combined linked list. Okay, so what I can do is I can check what is the smallest number. So the smallest number in these two linked lists would come at the beginning of the linked list, right? Because these two linked lists are sorted themselves. So the smallest number either would be the first number in my first linked list or the first number in my second linked list. So I just need to compare these two numbers to find out the smallest number in my combined linked list. So let us take two pointers, head 1 and head 2, that we will be using to compare values and find out what value will come first and next and so on. So when we compare head 1 and head 2 value, I see that head 1 value is smaller. So I safely say that this head 1 value is the smallest number that will be coming in my combined linked list. So now that I have established that this is the smaller number, what I can do is I can create a new node with the same number, right? I can create new nodes with the same values, with these values, and that will create an absolutely new linked list for me, but that would be taking up some extra space if we are creating a new linked list. We can also, what we can do is just change the links in these linked lists to create a combined one. So how can we do that without creating new nodes? Okay, without actually creating new nodes, how can I just combine these two linked lists? So to do that, let's first take a dummy head node. So we'll take a dummy head node, okay, with some random, value -1 or 1000, -1000 or something. So we'll have some dummy head node, and this dummy head node, in front of this dummy head node, will actually start our combined linked list. Okay, so when we find out from head 1 and head 2 which of these two are smaller values, smaller value is 1. So in front of dummy head node, let's also create another pointer head 3. Okay, that head 3 will be used to traverse the combined linked list. Okay, so head 3 will make it point to 1, okay, because we've established that that is the smallest number, so it should come in the front of our combined linked list. Okay, and now what I need to do is I'll move the head 3 forward, the head 3 pointer, and also move the head 1 pointer ahead. Okay, because I've already covered this number, so I'll move the head 1 pointer ahead. Now I need to find the second smallest number that will come in my linked list. So again, the second smallest number either would be at head 1 or head 2, right? I compare these two values 2 and 3 and I know that head 1 is pointing to the smaller number. So in front of head 3 I put 2. Okay, and again I'm shifting my pointers. So head 1 will come here and head 3 will come here. And now again I compare head 1 and head 2 values. Now out of head 1 and head 2 I know head 2 value is smaller, 3 is smaller. So in front of 2 I will have 3, right? And now I will move head 2 pointer forward and head 3 pointer. Alright, now again we compare head 1 and head 2. Out of head 1 and head 2 I know head 2 is smaller, so we make head 3 point to the smaller value, which is 4, and we move the head 2 and head 3 pointer. So head 3 will come here and head 2 will point to null. I cannot compare head 1 and head 2 values because head 2 has become null, right? So whenever any of these pointers, head 1 or head 2, when any of these pointers become null, that's when we just say make head 3 point to head 1, okay, which is not null. So what I'm basically saying is, if out of head 1 and head 2 any pointer becomes null, so we know that that linked list has ended there. So in front of the head 3, which is keeping track of the combined linked list, we'll just put the other linked list which has not ended yet. So here head 1 linked list had not ended, so we'll just put head 1 in front of head 3. Okay, and this will be our combined linked list, and we can say that the combined linked list head would be given to us by dummy head node next, right? This is dummies next. This is the dummy head node, and the dummy head node's next pointer will give us the head of the combined linked list. So once again, I'm trying to explain to you. Okay, you already have understood what exactly we're doing here, right? We're just comparing the value starting from the front, where of the two linked lists, we're comparing the values, and whatever is smaller, that I'm putting in my combined linked list. But what you really need to understand here, that we're not creating these nodes again. What I'm actually doing is, when I'm comparing 1 and 3 and I know that 1 is smaller, I'm just making dummy head nodes next point to 1. And then when I'm comparing 2 and 3, right, so I'm just making 1 point to 2. And when I'm comparing 5 and 3, I know 3 smaller, so I'm making 2 point to 3, then 3 point to 4, 4 point to 5, and 5 is pointing to 6. So this is how I'll get the combined linked list with 1, 2, 3, 4, 5, 6 values. So we're just changing the links here, and on what criteria or basis are we changing? We're comparing the values starting from the start of the two linked lists. Why? Because these two linked lists are themselves sorted. Okay, so the smallest values would be present in the beginning of my linked list, and if one of the linked list reaches null, like for in this example, I reached null, head 2 reached null, meaning this linked list is empty, does not have any more nodes to compare. So I'll just put rest of the other linked list in my combined linked list. Okay, let's see this in code so that it's more clear. So we'll create a function here which will return the new head of the combined linked list. So node star merge linked list, and we'll be getting here the heads of two linked lists. Okay, let's call them head 1 and head 2. So the first thing we need to do is create a dummy head node, and I hope it's clear why we're creating a dummy head node so that we can create the combined linked list in front of this dummy head node. Okay, and let's create a pointer as well to traverse the combined linked list. Let's call it head 3, which will be starting from the dummy head node. Okay, so now while head 1 and head 2 are not null, what we'll see is we'll first of all check if head 1 value is less than head 2 value. If head 1 value is less than head 2 value, then that means head 1 will come first, like the node which is being pointed to by head 1 pointer will come first in my combined linked list. So I can say head 3 next would be head 1, and then I can just move the pointers ahead. So head 1 is equal to head 1's next. Else, if head 2 value is less, in that case I'll say head 3's next should be head 2, and head 2 will be moved forward. Okay, and at the end of this if else, we'll also move the head 3 pointer ahead. So head 3 will be head 3's next. This loop will end when either of head 1 and head 2 becomes null. So again I can check if head 1 is not null yet. So I'll say head 3 is equal to, or sorry, I should say head 3 next is equal to head 1. And if head 2 is not null, then I'll say head 3 next is equal to head 2. Alright, and the new head node would be given to me by dummy head node next, right? That's where our combined linked list would be starting. So let's check this. Taking an example, we've created a linked list here with the values 1, 2, 5, 6, another linked list with the values 3, 4, and let's call our function merge linked list, where we're passing head 1 and head 2, and this function would be returning to us the head of a new linked list, combined linked list. So we can call the traverse function on that to see the combined linked list. So you see here, this is the first linked list, the second linked list, and this is our combined linked list which has the sorted values. Okay, so that's how you sort two linked lists such that, you combine two sorted linked lists such that the combined result is also sorted, and the time complexity here would depend on whatever will be the length of my shorter linked list, because that's what we're traversing here in the while loop. So if it is n, so O of n will be the time complexity for our solution. In this video, let's get started with some hard level questions on this topic, linked list. So if you were able to do the medium level questions, great, do revise them thoroughly before we start moving to these hard level questions. And remember one thing, linked list, you won't find a lot of questions related to this topic. You'll find some standard questions which are very important to this topic, and some of these questions we'll be seeing right now in this video. So the first really important question related to linked list is finding intersection. So if you're given two linked lists which are intersecting at some point, you have to find the intersection point if there is. Okay, it could also be that the list have no intersection point. In that case, you just have to return null. But if there is an intersection point, you need to find that out. So how do we go about solving this question? First of all, let's understand how these two linked lists could be intersecting each other. So I could have a linked list with these 4 nodes, and I can then have another linked list where 6 next is pointing to 3. So now here 3 is the intersection point for these two linked lists, right? This basically means that the 2 next is equal to 6 next, right? It's the same node after these two nodes. So in this case, we basically need to first detect if it is present and at what point they are intersecting. One approach could be if we can store the values or the nodes somewhere in some data structure of any one linked list, okay, and you've studied sets, then set is the data structure that would be most appropriate here. Let me tell you why. If I can create a set here and store all of the nodes in my set, okay, so what I'll do is I'll go through any one of the linked lists. Let's say the first linked list, I'll go through it, I'll traverse it, and I'll put all of my nodes here in my set, okay. So the set will be of type node star, and I'll put all of my nodes, not just the values, the nodes, I'll put in my set. Now, once I've done that, I can then traverse the second linked list. I'll traverse the second linked list, and while traversing this linked list, I can check if any of these nodes are already present in the set. So I'll check for 5, it's not present, 6 is not present, but when I come to 3, I'll see that it is already present in my set. That means this is my intersection point. But also, why are we using set here? That's because searching in set requires O of 1 time complexity, okay. So when I'm going through the second linked list and I'm checking if 5 is present, if 6 is present, then that operation will just take O of 1, okay, constant time complexity. So the search operation is inexpensive in set, and that is why set would be the right data structure here if you want to follow this approach. But the downside here would be the space complexity, right? We would require some extra space here for the set to store the nodes of any one linked list. So that is though a good solution. We require a better solution where we don't have to use any extra space, okay. So if you're not using any extra space, let's try to think in another angle, okay. Is there any way that while traversing these two linked lists, I can check that these two linked lists are intersecting at some point or not? Let's see. Let's think about it. If I start traversing, for example, I take a pointer 1 here and I take a pointer 2 here, and I start traversing and comparing pointer 1 and pointer 2 nodes. So I know 1 and 5 are not same. So I move the pointer 1 ahead, pointer 2 ahead. Now again, 2 and 6 are not same. But now when I move pointer 1 ahead and pointer 2 ahead, I can see that pointer 1 and pointer 2 are pointing to the same node. Then that means that we have an intersection in our linked list. This way we have found it, but there's a catch here. This solution only works if the length of the linked list is the same, right? So here both of these linked lists have 4 nodes, right? So that is why when we start our pointer 1 and pointer 2 at the heads of the two linked lists, while traversing at some point pointer 1 and pointer 2 will meet each other. But let's say we don't have 5 here, okay. I just have 6 in my second linked list. Now if I see and I try to follow the same approach, pointer 1 at 1 and pointer 2 at 6, okay. Now 1 and 6 are not same, so I move these pointers ahead. So pointer 1 will come at 2 and pointer 2 will come at 3. And still they're not same, so I'll move ahead. Pointer 1 will come at 3 and pointer 2 will come at 4. So in this case, when the lengths of my linked list are unequal, in that case even if there is an intersection, the pointer 1 and pointer 2 will never meet each other, right? Because we're starting both of these pointers from the heads, and the head is not equidistant, not at equal distance from the intersection point. However, if by some way we can make this possible, that pointer 1 and pointer 2, we start from the point that is equal distance from the intersection. So for example, pointer 2 is at distance 1 from the intersection. If somehow I'm able to also bring pointer 1 at distance 1 from the intersection point, and now if I start traversing my linked list and seeing if pointer 1 is equal to pointer 2, at some point pointer 1 and pointer 2 will meet. Now the problem becomes, how do I move my pointers at a distance which is equal from the intersection point? Now I don't know the intersection point, right? I don't know the intersection point. That's what we're trying to find. So it's not possible for me to find, the distance from which I cannot take the intersection point basically as my, the goal from which I need to find equal distance. But can I take the last node, the end of my linked list, from where I am finding equal distance? Because if there is an intersection point, okay, for example here it's 3. After 3, the rest of the linked list will also be, common to both of the linked list, right? Whatever nodes I have after 3 will be common to both of the linked list. So this part of the linked list, whatever it is after 3, 1 or 2 or 3 nodes or 0 nodes, that part is common to both of my linked list. So if I start seeing the distance from the last node, I know where the last node is. Okay, I know where the last node is. And from here, I want my pointer 1 and pointer 2 to be at equal distance from the last node, because I don't know where the intersection point is, so I cannot judge through the intersection point, but I know the last node, so I can judge from there. So from the last node, I want to put pointer 1 and pointer 2 at equal distance. So how do I do that? Now again, there's an easy way to do that. First of all, I need to find the lengths of both of my linked lists. So in my first linked list has 4 nodes and my second linked list has 3 nodes, right? Let's call this L1 and L2, length 1 and length 2. Now I don't need to move both pointer 1 and pointer 2, right? Whichever is the longer linked list, I only need to move the pointer for that. So in this case, the first linked list is longer, so I need to move pointer 1. Okay, let's first have pointer 1 here. I need to move pointer 1 because the linked list 1 is longer. Now how many steps do I need to move my pointer 1 so that it is at the distance which is equal as pointer 2 from the end? So pointer 2 I know is at distance 3 because there are 3 nodes. So I also need to bring pointer 1 at that. What I need to do for calculating the number of steps, I just need to calculate L1 minus L2. In this case 4 minus 3, which is equal to 1. So pointer 1 I need to move by 1 step. Okay, that means pointer 1 will come here and then I can start comparing. Okay, let's take another example so that this is more clear to us. This is my linked list 1 and this is my linked list 2. Okay, and I have my pointer 1 here, pointer 2 here. So the first thing that we need to do, let's actually just have one node here. Okay, so the first thing that we need to do is find the length of the linked lists. So the length of the first linked list is 1, 2, 3, 4, 5, 6. So 6 nodes. This is L1. and L2 is equal to 4. I know now L1 is longer than L2. So I just need to find L1 minus L2, which will be equal to 2. Then that means I need to move my pointer 1 by 2 steps. Okay. So 1 and 2. So my pointer 1 will come here. And now that I have moved my pointer 1 by k steps, okay, where k is equal to the difference in the length of the linked list. Now if I start checking pointer 1 and pointer 2, are they equal? They are not. So I move pointer 1 and pointer 2 ahead. Pointer 1 and pointer 2, are they equal? Yes, they are. That means we have found the intersection point. Okay, so once again, what's the intuition behind this solution? The intuition is if we can get the pointers at equal distance from the intersection point and then we start checking, we'll eventually get to our intersection point. And now we cannot get the pointers from the intersection point because we don't know the intersection point. So instead of calculating distance from the intersection point, we calculate distance from the end of my linked list. So from the end of my linked list, I want both of my pointer 1 and pointer 2 to be at equal distance, and if then they meet each other, whatever point they meet at, that will be my intersection point. Okay, so I hope that is clear. Let's see this in code now. In our function, we'll be returning the pointer to the node, which is the intersecting node. So let's keep the return type as node star get intersection node, where we are passing the heads of our two linked list. Okay, so the first step was to calculate the length of the linked list. So for that, let's write another function, int get length, where we'll pass the head of a linked list and it will return us the length. Why are we writing separate function for it? Because then we can use the same function to calculate length of both of my linked list, right? I don't have to write repeated code then. So let's create a variable n equal to 0, and let's create a temp pointer which will be starting from head. Now while temp is not equal to null, we'll just do n plus plus, we'll increase the value of n by 1, and we'll also move the temp pointer ahead by 1 step. Okay, and at the end of this, we'll return the value of n, which will give us the length of our linked list. Okay, so just like what we do in traversal, we've done the same thing, and we're just calculating the length of our linked list. Let's say the length of first linked list is L1 and the length of second linked list is length 2. So now we need to check which one is longer, L1 or L2. If L1 is more than L2, then the pointer in L1, let's call it pointer 1, would have to be moved ahead by k steps, where k is equal to L1 minus L2. So let's also define pointer 1 and pointer 2 outside, pointer 1 and pointer 2. So if L1 is more than L2, meaning the first linked list is longer, in that case, my pointer 1 will be at k steps after the head 1. Okay, let's calculate k also. K will be equal to L1 minus L2 because L1 is more. So pointer 1 would be k steps after head. Okay, so let's create another function for that as well, which will basically return us a pointer after k steps from head. Let's call this move k steps. Okay, where we are passing the head of the linked list and we are passing k. Alright, let's create a pointer which is at head. And while k minus minus, we can say while k does not become equal to 0, we'll keep moving the pointer ahead. Okay, and finally we'll return this pointer. So basically this function is returning to us a pointer which is k steps ahead of head. So move k steps where we'll pass head 1 and the value of k, and pointer 2 would be at head 2. So I don't need to move pointer 2 anywhere because this is the shorter list. Else, if L2 is more, okay, in case the second linked list is longer, in that case our k will be equal to L2 minus L1. Here pointer 1 will be at head 1 and pointer 2 will be calculated by moving k steps from head 2. So we now have pointer 1 and pointer 2 at equal distance from the end of our list. So now what we need to do is compare. While pointer 1 and pointer 2, while they don't become null, we'll keep checking and see if pointer 1 is equal to pointer 2. If they become equal, then that means I have found my intersection point and I can return pointer 1 or pointer 2 here. Else, I'll just move these pointers ahead. Pointer 1 is equal to pointer 1 next, and pointer 2 is equal to pointer 2's next. And if I get through this entire loop without returning true, without pointer 1 and pointer 2 meeting anywhere, then I can just return false, or not false, let's return null here. That means there is no intersection point. Okay, so again what we've done here is, first of all, calculated the lengths of our linked lists and then check which of these linked list is longer. If L1 is longer, we calculate L1 minus L2 and we move pointer 1 by k steps ahead of head 1. If linked list 2 is longer, that means L2 is more than L1, then we move pointer 2 k steps ahead of head 2. And finally, once we have head 1 and head 2 in the positions at the points, pointer 1 and pointer 2 at the points that we want, then we start checking, and if at any point pointer 1 and pointer 2 meet, then that means we found the intersection point. If they don't, then that means there is no intersection point. Alright, so we have a linked list here, we have another linked list here. Let me add an intersection point by saying that head 2's next. That means 5's next, make it equal to head 1's next. Okay, and let's see what this looks like, our second linked list. And finally we'll check, let's say node star intersection node is equal to get intersection node for head 1, head 2, and if this intersection node is not null, if it is not null, then print its value. Else, if it is null, then we can just print no intersection point. Okay, so this is our first linked list, this is our second linked list, and you can see 3 is the point where these are meeting and we get 3 as the answer. If I make it meet at 4, okay, now you can see 1, 2, 3, 4, 6, 5, 4. So they are of different lengths and they are meeting at 4. So it is returning to us 4, which is the intersection point. let me remove this, remove the intersection. So the first linked list is this, second linked list is this, and there is no intersection point in these two linked lists. All right. And what would be the time complexity for this? First of all, we'll require some time complexity for calculating the length of the linked list. Let's say n and m are the length of the two linked lists, and then if n is more than m, then we'll have to move n minus m steps, and then finally we'll have to move m steps, meaning for when we are checking if we get any intersection point or not, right? So this would come out to be O of n plus 2n plus m, which is basically O of n plus m only, right? And we're not using any extra space here. Let's move to the second question for today. The second question says, given the head of a linked list, reverse the nodes of the list k at a time, okay, and return the modified list. So let's understand what k at a time means. So for example, if we are given k is equal to 2 and we are reversing the list k at a time, then that means we are first reversing the first k nodes, then the second k nodes, and then the rest of the nodes. Okay, basically k nodes we have to reverse at a time, and then the entire list should be joined as well. Okay, so for example, if I have this linked list, now we've already seen how to reverse, right? We know how to reverse a linked list, but we saw how to reverse the complete linked list. Now what we need to do is just reverse k nodes at a time. At first, we'll have to reverse these two nodes if k's value is given to us as 2. So first of all, we'll have to reverse these two nodes, then we'll have to reverse these two, and then we'll have to reverse these two. Okay, so the output would be something like this, where 2 is pointing to 1, okay, 4 is pointing to 3, and 6 is pointing to 5. This should be easy, right? If we traverse the list in k parts, we should be able to reverse it. How do we connect these parts? Okay, these part of the linked list or sub list which is of k length. So if I'm just given this part of the linked list, I can easily reverse it. I already know how to reverse it. If I'm given this part of the linked list, I can reverse it too. But how do I connect these two parts? That's the tricky part. That's what we need to think about. An easier way to do this could be through recursion. Let's take example of recursion here, because this is something that we have to do repeatedly. Okay, for every k nodes we have to reverse. So what if I say that let's take help of recursion to reverse rest of my n minus k nodes. So n is the length of my linked list. First k nodes I will reverse iteratively, like I have shown you how to do this. And let's ask recursion to reverse the rest of my linked list, which is n minus k nodes. If we can do that, what will happen is, let's say we were able to reverse this part. Okay, first k nodes we were able to reverse. So then that means this would look like something like this, where 2 is now pointing to 1 and 1 would be pointing to null. The rest of the linked list, if recursion can reverse that for me. This is the rest of my linked list that is reversed. If recursion can reverse the rest of the linked list, then can I connect these two parts? Yes. How? Because recursion will give me the new head. The new head would be 4 here, right? The new head for the n minus k nodes. Instead of 1 pointing to null, if I can make this point to, this was my original head. If I can make the original head point to the new head, then I have joined my two lists, right? This is the part that is reversed by recursion, and this is the part that has been reversed iteratively by us. Through recursion, we'll be expecting the new head of the reversed n minus k nodes. And then we'll make the original head point to the new head to connect these two parts. And that's how we can have our output, right? Let's try to understand again from scratch. So this is my linked list, okay. What did I say? I said first we'll reverse the first k nodes iteratively. Okay, so 1 and 2 will reverse. And how do we reverse that? We reverse that using help of 3 pointers, previous, current and next. So I'll say, let me write it down here. So I'll say my current is at 1 and my previous is at null. Okay, and my next will be here at 2. So now the first step is to change the link between current and previous to reverse it. So I'll make the currents next and change it to point to null. And then I move my pointers ahead. So my previous will come where my current was and my current will come where my previous was. So, and where would the next go? Right now 2 is pointing to 3, so next would go here. So now I change this link, alright, I change this link and make the current point to previous, current's next point to previous, and then move my pointers ahead. So now my previous would be at 2 and current would be at 3. Okay, so now I have reversed 2 times. I've basically changed the current's link, make it point to previous, which is basically the reversing of the link here. I've done that 2 times. Okay, so for k nodes I have done the reversal, right? For 1 and 2 I have done the reversal of the links. K nodes I have reversed. Now what I need to do is I need to call the function recursively for rest of the n minus k nodes. Now how do I call the function recursively for n minus k nodes? So for n minus k nodes, for reversing that, I'll have to pass the head of that n minus k nodes. Now here, if these are the n minus k nodes, this list is starting at 3, right? And I just saw that after reversing first 2 nodes, the current pointer would be at 3, right? So basically 3 here is the n minus, or not n minus k plus 1th node. Okay, k nodes I have reversed. After reversing k nodes, my current pointer would be pointing to k plus 1th node, right, which in this example is 3. So that will become the head of the rest of the linked list. Okay, what is the rest of the linked list? 3, 4, 5, 6. This is the rest of the linked list. So this part of the linked list now I am passing to the recursion function recursively. And what will recursion do? Recursion will reverse this list for me. Let's discuss that as well. So how is recursion going to reverse that? Again, it is going to take the first n nodes. Okay, it will reverse the links for the first n nodes. So what will happen is 3 will be pointing to null and 4 would be pointing to 3, just like what we had seen with 1 and 2. And it will call recursively for the rest of the nodes. Okay, and now 5 would basically become my head of the rest of the nodes. Okay, again here I have covered again k nodes. So again 5 would become my k plus 1th node. So again I'll call the recursive function for 5, and what it will do is it will again reverse these 2 nodes for me. It will make 5 point to null and 6 point to 5. Now I can see recursively what is happening. K nodes are getting reversed. But now how am I connecting these k nodes? Okay, Let's try to understand that. So let's assume when I call the recursive function for rest of the k nodes, I call the recursive function for rest of the n minus k nodes, I get the reversed linked list for those n minus k nodes, okay, k at a time. So how would that look like? That would look like something like this, right? This is the k at a time reverse linked list for this part of the linked list. So for example, let's assume that this is what is being returned to us by the recursive function. Now how do I connect these two parts together? The recursive function will return to us the new head. So we'll make the recursive function return to us the new head. So the new head for this would be 4 and the original head was at 1. So we'll make the head point to new head. So 1 is now pointing to 4 and we'll pass the previous pointer as the new head. We'll pass the previous pointer as the new head. So now if I redraw this, this is basically equal to 2 pointing to 1, pointing to 4, 3, 6, 5, and this is the output that we were looking for. So it might seem complicated, the solution, because we're using recursion as well here. Try to break it down, okay? Try to break it down into steps. First step is we reverse the first k nodes. That shouldn't be difficult for us. We know already how to reverse an entire linked list. Here we just have to reverse k nodes, okay? We can easily do that. We have reversed the first k nodes. Now for the rest of the, let's write it down, okay? Let's write down the points. First step is to reverse k nodes. The second step is to call recursively for rest of the n minus k nodes. Call recursively or solve recursively for rest of n minus k nodes. Okay, and how do we do that? By passing the head of the rest of the list. What would be the head of the rest of the list? Well, that would be basically k plus 1th node. So first k nodes we have reversed. In the rest of the linked list, the head node would come out to be the k plus 1th node. For example, 3 in this case. So we'll pass that as the head and get the result of the rest of the n minus k nodes. Now the result of the rest of the n minus k nodes will return us new head. So we'll make the original head point to new head, okay, and our head of the combined linked list, okay, now we've combined the first k nodes with the rest of the n minus k nodes. Now the head of that combined linked list would be given to us by the previous pointer, okay, that we got when we were reversing first k nodes. So these 4 steps we are doing to reverse the list k at a time. Okay, let's try to do this in code so that we can understand better. So this will be a recursive function that will be returning us the new head. So let's keep that as the return type, reverse k linked list, and we are passing here the head of the linked list by reference and value k. Okay, so first step is to reverse first k nodes. So for that we create 3 pointers, node star previous, which is equal to null, node star current, which is equal to head, and node star next. Also, let's create a counter to keep track how many times we are reversing the nodes, because we only have to reverse k times, right, in the beginning. So int counter is equal to 0, and we'll create a loop where we're checking that the current pointer should not become equal to null, and also counter should be less than k. Okay, so we have another condition for stopping here. First condition is obviously that current should not become equal to null, and also counter is less than k. Okay, so we'll keep increasing the counter every time. We'll keep doing counter plus plus every time so that we only reverse k nodes, not more than that. The first step is to make next pointer point to current's next, and then change the current's next link to point it to previous. Then we shift the pointers, previous will come where current was and current will come where next pointer was. Okay, and once we've done that, now we have reversed the first k nodes. So the second step is to call recursively for rest of n minus k nodes. Okay, and to do that, we'll also check the, okay, so what did I tell you? The head of the n minus k nodes, the rest of the n minus k nodes, that will be given to us by the current pointer. Okay, current pointer will be pointing to the k plus 1th node. Current will be pointing to k plus 1th node. We'll call this function recursively reverse k linked list, where we'll pass the head now as current pointer and same value of k. Okay, and this will return us some new head. Okay, new head of the linked list, which is reversed k at a time. And while doing this, let's also check if current is not null. Okay, if current becomes null, if the linked list ends, then we don't have to call this function recursively again. So if current is not equal to null, only then we'll do this. We'll also do the third step, which is connecting first k nodes to rest of the reversed k linked list. So how do we do that? We say make the original head point to the new head. Make the original head point to the new head. And lastly, return the head of the combined linked list. So once I've combined the first k nodes to the rest of the linked list, I just have to return the combined head, the head of the combined list, which will be given to me by the previous node. Okay, the previous node will be pointing to my head of the combined linked list. Okay, let's see this. Reversing the linked list with k is equal to 2 value, and this will be returning to us head. So let's call traverse function for that. So this is my original linked list, and for k is equal to 2, we can see it has reversed the first 2 nodes, then the second 2 nodes, and then the rest of the linked list. Okay, we can also try for k is equal to 3 value. So for k is equal to 3, I see if the first 3 nodes reversed and then the next 2 nodes reversed. Okay, the rest of the nodes that are whatever present reversed. Okay, so this is how you reverse k nodes at a time in a linked list. Great, amazing. Let's move forward to the last question for today, that will be, given the head of a linked list, detect if a linked list has cycle in it, and if it does, we have to break that cycle. Okay, so very interesting question. This is basically 2 questions in one, and I've seen this question being asked in interviews, so let's pay attention to this. What exactly is happening here is, we are being given a linked list which might have a cycle in it. And what does it mean by having a cycle in it? That means that one of the nodes is pointing to another node that is coming previous to it, right? So you can see 5 here pointing to 3. So we can see here that this this linked list has a cycle in it, and if it does, basically we have to firstly detect it, and if it does have the cycle, we have to break the cycle. So first of all, let's focus on the first part of the question, which is detecting the cycle if it is present. And here we'll need to use some logic, okay, and let's try this. Okay, I'll give you a puzzle, and if you're able to solve that puzzle, then you will be able to solve this question as well. So the puzzle, very common puzzle, is, let's take a person Riya and a person Saksham. Okay, so Riya and Saksham, they are running. Okay, they start running at the same point. Now Riya is running at speed of 2x and Saksham is running at speed of x. At some point later in time, they both meet again, Riya and Saksham. How is that possible? How is that possible? Because Riya is moving at double the speed at Saksham. Then how is it possible then that these two people meet at some point later in time if they are starting at the same point at the same time? The solution to this puzzle is that Riya and Saksham are actually moving in a circular path. Okay, if you imagine it as a circular path, if they both start at the same point, okay, then even if Riya is moving at double the speed, in the time that Saksham will cover one loop, Riya will cover 2 loops, right? Because, why? Because Riya will cover 2 loops because Riya is moving at double the speed. So let's try to think and apply the same to this question. Can I say, if I have 2 pointers that are traversing this list, okay, one pointer is slow and another pointer is fast, where slow pointer is moving by 1 node and fast pointer is moving ahead by 2 nodes. Then if this linked list has a cycle, then at some point these 2 pointers will meet each other, right? And we can also validate that. Let's try to see. If I have this linked list, okay, and I start my 2 pointers here, slow and fast. Slow will move by 1 step, fast will move by 2 steps. So slow will come here and fast will come here, right? In the next iteration, slow will come here and fast will come here. In the next iteration, slow will come here and fast will come 1 and 2. So here. And I see slow and fast again are meeting at a common point, right? Then that means there is a cycle in this linked list. Okay, try to correlate with the example that I just gave you. That example said that, okay, if they are meeting, then they must be in a circular path, and I'm just saying the opposite of that here. If it's a circular path, then they must be meeting. So we'll use the slow and fast pointer approach here to detect if our linked list has a cycle in it or not. Okay, let's see the code for this. Bool detect cycle. So let's say we are getting past the head of our linked list and we need to detect if it has a cycle or not. So first of all, we'll create 2 pointers, slow and fast, note star slow and note star fast, both starting at head. Now, till when will we keep moving these pointers? We can say if fast or fast next or next of fast becomes null, then that means there is no cycle in it, right? So if fast and fast next, while they do not become null, we'll keep moving the 2 pointers. If if the linked list does not have any cycle, then at some point fast pointer or the next of fast will become null and this loop will break. Okay, till then we'll keep moving slow by 1 step and fast by 2 steps. Right, we'll keep moving the 2 pointers by 1 step ahead, and then we'll check if slow is equal to fast. So I'm not checking first, because if I check here, of course they both are starting at head, so they will, you know, be at the same point. But I want to check if if I've started moving these 2 pointers slow by 1 step and fast by 2 steps, after that are slow and fast pointers meeting at some point? If they are, then that means there is a cycle in my linked list, and if they don't meet anywhere, then that means there is no cycle. Okay, so let's see, I've created a linked list here. Let's add some more values. I'll create a cycle in this. Let's say head of next of next of next of next of next. Okay, so let's say I'm making 5.23. Okay, and now don't call the traverse function on it, by the way, after creating the cycle, because if you do, your traverse function will just keep running indefinitely, right? Because there is no null, it won't be able to find null anywhere if it has a cycle in it. So let's print the output of this detect cycle, where we're passing the head. So this returns 1, that means there is a cycle, and if I remove this line, then it is returning 0, that means there is no cycle in my linked list. Okay, so now I have seen how to detect a cycle in a linked list, but how do I remove the cycle? That's the second part of the question that we need to solve, removing the cycle. And to remove the cycle, what I need to do is, to remove the cycle, I basically need to find where the cycle is starting. For example, here 3 is the point where the cycle is starting. If I can get to this point, and I make this point to null, if I make 5 point to null, I know that 5 is pointing to 3 and that's where the cycle is starting. So if I can change that and I can make 5 point to null, then the cycle is removed in my linked list, right? Let's also understand with the help of another example. So let's say we have another linked list with 7 nodes, where 7 is pointing to 3 and that's where our cycle in our linked list is starting. Okay, now here again, if we start our slow and fast pointers, they will meet at some point and we'll know that there is a cycle in this. What we need to find now is at what point the cycle is starting, so that we can break the cycle. Now for this we use the Floyd's algorithm, which basically says that the point at which slow and fast pointer meet, okay, from that point and from the head of my linked list, from these 2 points, okay, so for example, if slow and fast are meeting here, I'll also show you. So this is the point where slow and fast pointer meet, and this is the head of my linked list. So from these 2 points, the distance of the start of the cycle is equal. And let me prove that to you. So for example, if we start our slow and fast pointer here, okay, in the next we'll have slow here and fast here. Next iteration we'll have slow here and fast here. Next iteration we'll have slow here and fast here. Next iteration we'll have slow here and fast here. And in the next iteration we'll have slow here on 6th and fast also here. So slow and fast are meeting at 6. And here, from here, what is the distance till 3? The distance is 2. Basically I have 2 nodes from here till the start of the cycle. And from the head of the linked list also I have 2 nodes, okay, till the start of the cycle. And you can try this on any linked list, which has a cycle in it, and you'll be able to prove it, okay. And we can also prove this mathematically if you want. We can prove this mathematically that Floyd's algorithm works. Let's try to prove that, okay. And this part you can totally skip if you want to. But if you want to find out the mathematical proof for this Floyd's algorithm, let's see that. Let's first take that the distance from the head to the point where the linked list starts, let's take that as x1, and x2 is the length of the rest of the linked list. So basically this means that x2 is the length of the cycle that is being created in my linked list. Okay, and one more thing, the point where our slow and fast pointers were meeting. Okay, at 6 our slow and fast pointers were meeting. Let's say the distance from the start of the cycle to the point where these 2 pointers were meeting, let's call it x3. Okay, now let's try to find out what was the distance covered by a slow pointer, okay, till this point. What was the distance covered by it? First of all, it covered some x1 distance, okay, then it covered some loops, okay, some number of loops around the circle, so let's call it n. If it covered n cycles, so let's call it nx2 would be the distance. And finally it covered some distance x3, after which it met the fast pointer. The distance covered by fast pointer would be x1 plus some loops, some number of loops, let's call it m. So distance would be mx2 plus x3, after which it meets the slow pointer. Because fast pointer is moving at double the speed, which means fast pointer is moving by 2 nodes where slow pointer is moving by 1 node. So since fast pointer is moving at double the speed, the distance covered by the fast pointer should be double the distance that is covered by the slow pointer. That makes sense because it is moving by double the speed. So basically distance covered by the fast pointer would be 2 times distance covered by the slow pointer. So I can say x1 plus mx2 plus x3 is equal to 2 times x1 plus nx2 plus x3. And if you solve this, what you will get is x1 is equal to m minus 2n x2 minus x3. You would see x1 equal to this, okay, and this m minus 2n would be some integer constant, so let's just call it k, okay. So x1 is equal to k x2 minus x3. K x2, what this stands for? Basically k loops, so that's the difference covered. I can also, after I cover, if I start at this point and I'm covering x2 distance, I'm coming at the same point, right? If you cover the entire circumference of a circular path, you come at the same point. So I can say x1 is equal to x2 minus x3, because after k minus 1 x2 you will come at the same point, right? So after that I can say x1 is equal to x2 minus x3. Now this is what proves our Floyd's algorithm. It says x1, which is this distance, is equal to x2 minus x3. And what is x2 minus x3? This distance is x2 minus s3. Basically the distance between the point where slow and fast meet and the point where the cycle starts. So x1 is equal to x2 minus x3, and this is your Floyd's algorithm proved. So this is not important, just for your curiosity if you want to know how this actually works, but we are using this logic to find the point where the cycle is starting here so that we can remove the cycle. Okay, first we move the slow and fast pointer to find the point where they are meeting. Then we start from the head pointer. We can create another pointer and start traversing from the head and keep moving till we are able to find the common point, which will be where the cycle is starting. Okay, let's see this in code. Void remove cycle, where we'll be given the head of our cycle, and first of all let's create our slow and fast pointer, which will be starting at head, node star slow and node star fast, and let's use a do while loop here. So while slow and fast, till the time they don't meet, I know they will meet for sure because I've established that there is a cycle in this linked list. So till the time they don't meet, I will keep moving. Slow is equal to slows next and fast is equal to fasts next. So I'll keep moving these two pointers, fast next. Okay, so slow is moving by one node and fast is moving by two node till the time slow and fast move. So now slow and fast would have met somewhere. Now I start another pointer from head. Okay, let's move the fast pointer only. I'll move the fast pointer to my head, and now what I need to do is, while slows next is not equal to fast next, so at some point slows next, the next node for slow and the fast will become the same. This will be just before the start of the cycle. So till that time I'll keep moving my slow and fast pointer by one step ahead, and at the point where slows next and fast next is same, that means slow is pointing to the node just before the cycle is starting. Okay, so I'll say make slows next equal to null, and this will remove the cycle that is present in my linked list. So let's see here, let's turn it into an if condition. If my linked list has a cycle, then I'll call the remove cycle function for my linked list. Okay, and after removing it, then I can call the traverse function for it, right? Because now there is a null present in my linked list. My linked list will be ending somewhere now. Else we'll just print no cycle detected. Okay, so here the condition should actually be slow is not equal to fast, right? Because till slow is not equal to fast, we want to keep moving, and whenever they become equal, that's when we want to stop. Okay, and also why am I using do while loop here instead of just simple while loop? Because if I use a while loop here, then in the beginning slow and fast are at the same point, so the while loop will never get executed, right? So that's why we're implementing do while loop here. Why aren't we able to see any output? Let's check. Let's try printing the value of fast. Yep, okay, working now. So we are able to see 4 is the point where, slow and fast were meeting here in this cycle, and after removing the cycle, I can see my linked list here printed. Okay, so perfect. So in this lecture, we are going to see another type of linked list. What we have seen so far is a singly linked list, and why it is called a singly linked list? Because every node in a singly linked list has one link, where it is pointing to its next node in the list. In doubly linked list, as the name suggests, every node will not have one but two links. One link will be to the next node and one link would be to the previous node in my list. Alright, and that is why it is called a doubly linked list. Now, what are the advantages of having two links for every node? Now, you see, you can imagine a doubly linked list to look like something like this. For example, if you have three nodes, here each node would be pointing to its next node and also its previous node. So you see double links for every node, and this is an example of a doubly linked list. Here the first node's previous would be pointing to null, just like the last node's next would be pointing to null. Okay, so again, but we will have the first node be pointed to by head so that we know where our linked list, doubly linked list is exactly starting. Okay, so this is how you can imagine a doubly linked list. Now, what are the advantages of having a doubly linked list? So in a doubly linked list, we can traverse in both directions. Right? In a singly linked list, what was happening so far? We were only able to move in the forward direction because every node only had access or link to the next node in the list. Okay, so it was not possible for me to move backward. But here, since every node also has a link to its previous node in the list, we can also move in the backward direction. We can also traverse our linked list in the backward direction. Okay, so this is one of the advantages that we have. Another advantage is the insertion and deletion becomes easier. Why? Again, because we have links to the previous node and we have links to the next node. So insertion and deletion would become easier here since we're able to move in both direction, forward and backward from any given node. But considering these advantages, there is also a disadvantage. There is also a disadvantage, that is the extra space occupied by the second link. Okay, in doubly linked list we have two links, so there would be some extra space that is being used by the second link. So that is one of the disadvantages when we are using doubly linked list over singly linked lists. Okay, but considering this, we will find a few examples where we need to traverse a linked list in both directions, and that's when a doubly linked list would come in handy and save us. So let's move forward and see how would we define a node, a single node in a doubly linked list. What are the things that might change here from the singly linked list? Okay, let's first revise what was happening in singly linked list. So in a singly linked list, every node had two parts. First was the data part or the value part, which is storing some value for us, and the other part was the next part, which was basically a pointer to the next node in the list. Now in doubly linked list, we have a third part to this node, which is called previous, and this is the link to the previous node in my list. Alright, so this basically means that in doubly linked list, every node will have three parts. Okay, so these nodes will have some values. The previous of the first node, okay, the first node, which let's call it the head node where our linked list is starting. The previous of this head node will be null, and the next of this node will be pointing to the next node in my list. Again, in the second node, the previous would be pointing to the first node, and the next would be pointing to the third node. For the third node, the previous would be pointing to second node, and the next would be pointing to null. Okay, so this basically means that our list ends here. So whenever we see a node which has for which the next pointer points to null, that means my list is ending there. That means that is the last node of my list. And although the first node we can check from the head, head pointer will always have on the first node, but also another another unique thing about the first node will be the previous pointer of the first node will be pointing to null. So this is how our node definition would look like in a doubly linked list. Let's try to implement this, and we'll also see the traversal side by side. Okay, so we sort of know how to traverse a singly linked list the same way we'll be implementing here in doubly linked list. But the difference would be here we will be able to do not just the forward traversal but also the backward traversal. So first of all, let's create class node here for our doubly linked list. Okay, we're calling it the same. If you want, you can call it another node, but still, like when you talk about singly linked list, doubly linked list, or any other type of linked list, the node is a node, just the definition of it will change. Okay, so in this case, in the definition, first of all, we will have some value that we'll be storing in our node, and then we will have two pointers. These pointers will be of type node star because they'll point to another node in my list. So first one node star next, and another one node star previous. Okay, let's also create a constructor here. So if I'm passing any value d, so it should put that value in my variable value, and next and previous we'll make it null initially. Okay, so this is what my node definition looks like in a doubly linked list, for a doubly linked list. Now let's try to create a doubly linked list using this node. Okay, so I'll create node star n1 is equal to new node with some value 1, and node star n2 is equal to new node with some value 2. Okay, and now here if I make node 1's next point to node 2 and node 2's previous point to node 1. So we've connected my two nodes here in doubly linked list. Also, let's make this public so it's accessible. Alright, so n1's next is n2 and n2's previous is n1. Okay, and let's also create a pointer head which will be at n1. So here I've created a doubly linked list which has two nodes, n1 and n2, and if you want to print this doubly linked list, let's write a traversal function for that. Okay, first of all we will write traversal for forward. Okay, let's call it forward traversal, where we'll be passing the head of my linked list, and to traverse my linked list I'll create a temp pointer, make it point to head. Now we'll keep moving this temp pointer ahead till temp reaches the last node, or let's say till temp reaches null. We'll keep moving temp forward. Okay, and we will also print the value of temp. Alright, so what are we doing here? We've created a temporary pointer temp, and we're using that to traverse our entire linked list. Right, in this linked list we are traversing till temp reaches null, because when we start traversing our linked list, at some point when we move to the next, when it is at the last node and it will move to the next of last node, it will reach null, and that's when this loop will break. Till that time we will keep printing the value of temp, and we will keep moving our temp pointer ahead. Okay, at the last I'm just printing null so that we know our linked list has ended here. And let's call this function forward traversal for head. Okay, so this is the linked list that is being printed here. I haven't added arrows here. Okay, if you want, we can add arrows, but keep in mind that these arrows are bidirectional, right? Both ways these arrows would be going from 1 to 2 and from 2 to 1, right? But not for null, obviously. From 2 to null there only be one link, no link from null to 2, obviously. Okay, so I don't want you all to get confused here, so we'll just keep it at that. Okay, this is my doubly linked list. And so another thing that I want to mention here is, here we are only making use of the head pointer. In some cases we can also use a tail pointer which will be pointing to the last node of my list. And where would that be beneficial to us? When we want to access the last node of my list, because right now if I only have the head, I'll actually have to use a pointer and go till the last node. But if I have tail pointer, then I already know what is the last node and I can traverse back from it. Okay, so here I'm not taking the tail pointer, but you can do that if you feel like in any particular question, having a tail pointer to the last node of the doubly linked list can decrease your time complexity or can help you greatly. Okay, so coming back here, let's write a function for backward traversal as well. Node star head, node star, again we'll have to have a pointer, temp pointer, that will be starting from head. So for backward traversal, first of all we'll need access to the last node, right? So for that, let's move our temp pointer till the last node, till temp of next doesn't become null. And when will next of temp become null? When will next pointer of any particular node become null? When we are at the last node, right? So till that happen, we'll keep moving our temp pointer ahead. Now we are at the last node, so we can start traversing back. Again we'll keep a condition while temp becomes null, because it will become null as well when we start traversing backwards. How? Let us see. If I keep doing temp is equal to temp previous, so at some point when it will reach the first node in my doubly linked list and it will go to previous of that, it will reach null, right? So in this case we'll keep while temp, and we'll also print the value of temp. And in the end, let's just print null, right? Because even if we are traversing backwards, even then at some point we will encounter null, right? Because the previous of the first node, the previous of the first node points to null. So let's call the backward traversal function here. So you can see this is the forward traversal of our linked list, doubly linked list, and this is the backward traversal that we have here. Alright, so this is how we can traverse a doubly linked list. Let's move forward and discuss now how insertion and deletion operations would become different when we're talking about doubly linked list. So starting with insertion, where we are talking about adding a node or inserting a node at the start of a doubly linked list. So let's assume we have a doubly linked list, something like this, and we want to insert a new node at the beginning. So first of all, we do have access to the first node through the head pointer, and our first step here while inserting would be creating the new node, right? Let's call this the new node. This is the new node that we have created. Now to insert it at the beginning, what I'll have to do, first of all, I'll have to make the new node's next point to my head. My head's previous point to my new node. Okay, these are two steps, and the third step would be to move my head pointer to my new node. Okay, so three things that I need to do to add a node at the start of my doubly linked list, and the time complexity here would be O of 1, constant time complexity, because we're not traversing our linked list. So let's write the code for this. Void insert at start, where we are passing our doubly linked list by reference, and the first thing, also in the parameter we miss the value, so we'll also pass the value of the new node that we want to insert. Alright, so first of all, let's create a new node. Node star new node is equal to new node with the given value. And once we have the new node, then what we want to do is, in the new nodes next, we want to add the current head node. In the head's previous, we want to add our new node. Okay, the new node's previous would be by default null, so we'll keep it at that. And finally, we'll move head to, not null, sorry, to new node. Okay, so now our head is at our new node that we've inserted. Let's test this. Insert at start, passing the head and passing some value 9, and let's check the forward traversal. So you can see 9 got inserted at the beginning of my doubly linked list. Next, let's discuss how to add a node at the end of my linked list. Okay, so considering this is our linked list, again our first step here would be to create the new node with the new value that is given to us. Let's call this new node, and here we would have access to the first node of my linked list through the head pointer, but I'll have to get access to the last node, because after the last node I need to insert the new node. So I can create a pointer temp and use it to traverse my doubly linked list till I reach the last node. I know I will reach the last node when its next becomes null. So after I have reached to the last node, what I'll need to do is simply in the last node's next, I'll put the new node. In the new node's previous, I'll put the last node, which is pointed to by temp pointer, and new node's next is already null by default, so we don't need to change that, and that is how we'll be able to add a node at the end. Again, here the time complexity would be O of n because we need to traverse to find the last node, but in case we had a tail pointer here at the last node, the time complexity would have been simply been O of 1 constant time complexity. Okay, so void insert at end node star head and the value that we need to insert. Okay, now to first of all let's create the new node. Okay, node star new node is equal to new node v, and to traverse to the last node we'll create a temp pointer starting at head while temp next. Okay, or we can also call it last node since we want to go to the last node using this pointer. So till the next of last node doesn't become null, we'll keep moving this pointer forward, and once we have reached to the last node, then in the last node's next I will put the new node. In the new node's previous I'll put the last node, and that will insert the new node for me at the end. Also let's consider an edge case. In case my head is equal to null, meaning my doubly linked list is empty, there is no node in my linked list yet. In that case, this line will throw an error when we try to access the next of null. Let's also consider edge cases here while inserting. Okay, in both of these cases, these can throw an error if my linked list is empty. Okay, how? So let's see if my head here is null. Okay, there's no node in my linked list yet. So when I try to access previous of head, it will throw me an error, right? So let's just say if my head is equal to null, meaning my linked list is empty, in that case my new node will become my head, and I can return from here. I don't need to do these steps. Or else another way to deal with this is if my head is not equal to null. Okay, if my head is not equal to null, then I'll perform these steps. If my head is not equal to null, meaning I have at least one element in my linked list, in that case we'll follow this approach. In the new nodes next, I will put my head, and in the head's previous I'll put the new node. Okay, and if my head is null, then all I need to do is just make my head pointer point to my new node. Okay, similarly here also this will fail when we try to access next of head if my head is null. So let's just say if my head is null, then we can just make head point to my new node and return. Okay, I don't need to do anything rest of this if my linked list is empty and I'm trying to insert at end. Okay, moving forward to inserting a node in the middle of my doubly linked list. Okay, so let's assume we are given some value k, which tells us the position at which we want to insert my new node. Okay, and let's say k's value is 3 or let's say 2. So first of all, for adding a node here, I'll have to create a new node. So I created a new node. Okay, now to add a node at k position, I'll first have to go till k minus 1 position. Okay, so this is my head and this is also my k minus 1th node. So I'll traverse till my k minus 1 node, and of course we'll keep a different condition if k's value is 1. In that case we are just trying to insert at the beginning, so we'll call that function. But for any value of k which is more than 1, we'll first go till k minus 1th node, and then for that node and for its next node, for the kth node, we'll have to change the links, right? What all will need to be changed? First of all, let's call this as temp. Okay, let's call this as temp node, and this is temp's next, right? This node is temp's next. So temp's next previous is right now pointing to temp. Okay, we'll make this point to, we will remove this and we'll make the temp next previous point to my new node, and we'll make our temp's next point to my new node, and then we'll change the links for new node as well. We'll make our new node's next point to temp next. So we'll do this, we'll not change this link. Okay, we'll first of all add links between temp next and my new node. So temp next previous should point to new node and new node's next should point to temp next. After I've done these changes, then I'll say temp next make it point to new node and new node's previous make it point to temp. Alright, so I've added all of the links now. Okay, I have all of the links between my k minus 1th node and new node, both my next and previous, and I also have all the links between my new node and k plus 1th node. Okay, one other edge case could be when k's value is equal to n, the number of nodes. So for example, if we have 4 nodes, okay, after including the new node, and I want to insert the node at 4th position, basically at the end of my list. Again, if you follow the same approach, I'll move first of all to the k minus 1th node, which will be this, my last node. Okay, this will be my k minus 1th node, and if I want to add a new one, first of all this next would be pointing to null. Okay, so this will be my temp next, and when I try to access temp next previous, it would give me error. Okay, so I'll need to keep a check. If my temp next is not null, only then I'll change its previous link and point it to my new node. Okay, else what I'll do is just make my new node's next point to null, and I'll change the links between these two nodes. Alright, so in doubly linked list, although the insertion, deletion, traversal, backward, it becomes easier, but a little bit of complexity increases because we need to take care of whenever we're trying to access the next of previous or previous of next node, we need to check if it is null or not. Okay, because if it is null and we do not add an edge case or a check for that, it will throw an error and break our code. Okay, and the time complexity here would be O of n depending on the k value. So let's just say O of k. So let's come to the implementation now. Void insert at middle, where we have our node star head, we have the value to be inserted, and we have the k position at which we want to insert the new value. Okay, so first of all, let's check if k is equal to 1. If k is equal to 1, that means we just want to insert at the beginning. So let's just call this function insert at start for the new value. Else, if k is more than 1, in that case what we'll do is, first of all, traverse to the k minus 1th node. So for that, let's create a pointer temp which is starting at head, and I'll create a for loop where this loop will traverse till k minus 1, and temp will keep moving forward till I reach my k minus 1th node. After I do reach my k minus 1th node, then I need to make changes between, first of all, the next node, which would be the current kth node, and the new node. Okay, so let's create the new node. Node star new node is equal to new node with the value v, and we'll say temps if temp next is not equal to null. In that case, make temps next previous point to my new node. We'll make our new node's next point to temp next. Okay, now we've made changes between the new node and the previously kth node. Now we will make changes between the k minus 1th node and the new node. So we'll say temps next, make it point to new node, and new node's previous, make it point to temp. So this is our code for inserting in the middle. Let's test this. Insert at middle head, and let's insert the value 3 at position 2. Okay, we didn't call the forward traversal. So this was our linked list, and we inserted the value 3 at position 2. If I insert it at position 3, I can see at position 3. I can also insert at position 4. Okay, so 3 is inserted now in the end, and I can also test for insertion at position 1. Okay, this is inserting it 2 times because we are not returning here. Alright, so make sure to return from here in the if condition if you are calling this function to insert the element at the start. Okay, so it's always good to test your code with all the different values so that you can test if you left out something. Okay, cool. So moving forward to deletion now. We've covered insertion. Let's move forward to deletion. First of all, deleting a node from the start of my linked list. So for deletion, again, we'll have to take care of both of the links. If you want to delete this head node, okay, I'll move my head pointer to the next node. Okay, first of all, let's make this pointer, node that needs to be deleted pointed to by a pointer. I can make a temp pointer, delete node, whatever, some pointer pointing to the node that I have to delete. Then I'll move forward my head to the new head after I delete my first node, and I'll make the previous of my head point to null. Okay, so you can understand it like this. I'll change this and make its previous point to null. Okay, because this is the first, it will be the first node now, so I'll have to make its previous should be pointing to null. Okay, and then I can get rid of my first node. So let's look at the implementation. Delete at start, node star head. So let's say temp is pointing to the head node that needs to be deleted. We'll move head to heads next, and then I can say heads previous should be pointing to null. And finally I can free up the temp node. Okay, again this code will throw an error if I only have one node in my doubly linked list. So I can add a check if my head is null or my heads next is null. Okay, in case my linked list is empty, or actually let's just consider the case where it has one node. Okay, let's assume that there will be at least one node if I'm trying to delete something. But if there's only one node when I'm trying to delete at the start, in that case I can just do free head and return. Okay, in that case I don't have to do all of this. So delete at start, forward traversal, let's check. Okay, we need to make this condition as if heads next is equal to null and not if it's not equal to null. Okay, so in this case 3 got deleted from the start, and now we have this as our remaining doubly linked list. Okay, so I hope you caught that. We just missed comparing head next with equal to null here. Okay, if we just put it head next, then what it was doing was it was checking that okay, this is not null, so I'll just free up the head and then my linked list was gone, right? If you free up the head, there's no linked list because you lose where your linked list is actually starting. Okay, so good catch here. Always take care of the condition that you add in if, and the time complexity here would be O of 1. Moving forward, deletion from the end. Here, while deleting from the end, we'll have to traverse to the end of the list. So we'll take a pointer temp, use it to traverse to the last node of my doubly linked list. Okay, and let's make temps previous. Let's say this will be my last node after deletion. So I'll make the last nodes next. I'll remove its next and make it point to null because the last nodes next should be pointing to null, and then I can free up my temp node. So void delete at end node star head. So first of all, a pointer to reach the last node starting from head while temp next is not equal to null. Till then we'll keep moving our temp pointer forward. Okay, now our temp is at the last node. This is the node that needs to be deleted. And what will be the new last node after deletion? That will be temp's previous. So I'll make the new last nodes next point to null, and then I can free up temp. Okay, and again we can add a condition, the same condition here. If we only have a single node in my doubly linked list, then I can just free that up and return from there. I don't have to do any of the else things. So delete at end, head, and let's check the forward traversal. So this was my linked list, and after deleting from the end, 2 is removed. Okay. Finally, let's see how to delete a node from the middle. So if I have a linked list, doubly linked list, which looks like this, and this is the node, the k value that is given to me. What do? First of all, let's traverse to the k minus 1th node. Okay, and let's call this temp, just like while inserting. Same way we'll traverse to the k minus 1th node. We'll make temp's next get pointed to by delete node, meaning this is the node that needs to be deleted. Now we'll have to change the link between this temp node and this node, which is delete nodes next. So this delete nodes next, before deleting it, we can make these changes using delete node pointer. We can say temp's next, make it point. We can edit this and say temp's next should point to the delete nodes next, and delete nodes next previous should point to my temp node. Okay, and once I have added these two links, then I can get rid of my delete node. Okay, and the time complexity here would be of k, depending on what is the k value given to us. So void delete at middle node star head, and we'll be given some k value which will tell us where exactly we need to delete our node. So let's check. First of all, traverse to k minus 1th node. So we'll start a traversal from head, and let's create a for loop starting from I is equal to 1 till k minus 1 I plus plus. I'll keep moving my temp pointer ahead. Now my temp pointer is at kth node. What will be my delete node? The node that needs to be deleted, that is temp's next, right? That's the kth node that needs to be deleted by me. Next we'll say my temp next should be pointing to my delete nodes next, and if my delete nodes next is not null, then my delete nodes next previous should point to my temp. Okay, because it could be that the k value is equal to the last node. Basically we're trying to delete the last node of my linked list. In that case, delete nodes next would be null, so we won't be able to access its previous. So we've added an if check here. Okay, so if it's not null, only then we'll make the delete nodes next previous point to temp. Okay, so now we've added both the links between temp and delete nodes next. Now we are safe to remove our delete node. Okay, and again we can add a condition here. If k is equal to 1, then we can just say delete at start and return. So let's call this delete at middle function, and let's delete at second position, forward traversal for my head. So this was my linked list 3912, and here I've deleted the element at position 2, so 9 got deleted. I can try at position 3, so 1 should get deleted. At position 4, 2 should get deleted, right? And position 1, 3 should get deleted. Okay, so it's working for all of the values. Cool. So we've seen here how insertion and deletion happens and how it is different from single linked list. So not much difference. The the way of traversal and changing the links remains the same. Just you have an extra link to take care of whenever you're inserting a new node or you're removing an existing node. Okay, so let's try and now solve some questions on doubly linked list so that this concept becomes even more clear and you become even more comfortable with this topic. So the first question is reversing a doubly linked list. So we've already done this for singly linked list, so approach would almost remain the same here, just the implementation would change a little. So let's imagine first we have 3 nodes, 1, 2, 3, okay, and these are the nodes that we need to reverse. So starting here, first of all you need to remember that the first node's previous would be pointing to null and the last node's next would be pointing to null, right? Now if you just imagine for the first node, okay, we need to reverse its links. How? Such that right now what is happening for this is its previous is pointing to null and its next is pointing to 2. We want to reverse this. We want one's next to point to null because it will become the last node in my reverse doubly linked list, and I want its previous to point to the current next node, which is 2 here, right? So let's start with the approach that we saw in singly linked list. Singly linked list we were taking 3 pointers to keep track. Here let's see if we do require in fact 3 pointers, or we would be able to solve this using less number of pointers. Okay, so first of all, with my first node, which is my head node, I'll keep a pointer current. Okay, now for the current pointer, I just told you what I need to do. I want to make its previous point to its next and its next point to its previous, right? So now first of all, if we change its next node and make it point to previous, so let's say we remove this link and we make one's next point to its previous, which is null. So I'll lose access to the rest of my linked list in that case. So I need at least 2 pointers here. Okay, so let's start with 2 pointers. Let's start with previous pointer and current pointer. Okay, previous would be pointing to the previous of my current. Now let's see if these 2 pointers would be enough for me to do the reversal. What I can do first is I can change the previous link and I can say remove this link, current's previous, and make the previous point to 2. Okay, and how do I access 2? 2 is current's next. So make current's previous point to current's next. Okay, I did that. Then I need to change the next link. So I remove this link and I say the currents next should point to previous. The currents next should point to previous, which was being pointed to by null. Okay, let me call this previous pointer and current pointer so that you don't get confused between the previous pointer that we have in the node and the pointer that we have here for traversal. Okay, so current pointer and previous pointer. So I made current pointers next. First of all I made current pointers previous point to current pointers next, and now I said current pointers next should point to my previous pointer, which was null. Okay, so I inversed the links for my current pointers. Now I need to move to the next node. So what I do is I will move my current pointer to its previous. I'll move the current pointer to its previous, and I'll move the previous pointer to current pointer's previous, which is this. Right? 2's previous is 1 and its next is 3. Alright, so now we inverse the links for 2. What we do first is change its previous link. So I'll say make current pointers previous point to current pointers next, which is 3, and make current pointers next point to current to the previous pointer, which is 1. Okay, and after doing this, again we'll shift the pointers. We'll say move the current pointer to its previous and previous pointer to current pointer's previous. Again the same thing will repeat. We'll first of all change current pointer's previous link, remove this and make the previous point to its next, which is null, and make its next point to previous pointer. And once I've done that, then I move the links again. I say move the current pointer to current pointer's previous. So current pointer is at null, and now when my current pointer reaches null, I know that my entire linked list has been traversed, so I stop here. Now what will be the new head? The new head would be this node 3, and how do I access that? If you see, before I moved the nodes forward, okay, this was my case where previous pointer was at 2 and current pointer was at 3. So when I move my current pointer here and I realize, okay, now my linked list has empty, then I can say my head pointer would be at previous pointers previous. Okay, the previous node of my previous pointer here is my new head node for my reversed linked list. Okay, so now you can see head is at 3, 3's next is 2, 2's next is 1, and 1's next is null. So we have reversed our linked list. Let's see this in code. Void reverse doubly linked list, where we are passing the head of my linked list. And for pointers, first let's create a current pointer that will be starting at head, and another pointer I'll create called previous pointer that will be keeping track of the node before my current pointer. So while my current pointer is not null, what I'll do is first of all bring my previous pointer to current pointer's previous node. Then I can change my current pointer's previous to point to current pointer's next node, and then change my current pointer's next node to point it to my previous pointer, okay, where its previously its previous node was. And finally, once I have done this, I've reversed the links, then I move my pointers ahead. So I'll say move my current pointer to current pointers previous. Okay, I can create another pointer, next pointer here as well, just like we had 3 pointers in singly linked list, but as you can see there is no need for that. For just 2 pointers, current pointer and previous pointer, we can reverse our linked list, because here like every node has already, you know, keeping track of its previous node and next node, so we don't need a third pointer here to reverse the list. And finally my head would be at my previous pointer's previous node at the end when my current pointer reaches null. So let's test this out. I've created a doubly linked list here with 5 elements. Okay, and let's first try to print this. Okay, so we'll do a forward traversal and let's also do a backward traversal. Okay, and basically the backward traversal and the reverse of my linked list should match, right? So I'll call the reverse doubly linked list function here, passing my head. So in this lecture we'll be looking at another type of linked list which is called circular linked list, after which we'll also see list in C++ STL. Okay, let's start with first of all what is a circular linked list. So far we have seen what is singly linked list, we have seen doubly linked list. The difference was that in singly linked list every node was just pointing to the next node in the list, but in doubly linked list every node was pointing to the next node as well as the previous node in the list. Now what is a circular linked list? A circular linked list is a linked list in which the last node points to the head node. Meaning if I have a linked list like this where the first node is the head node, if I make the last node, okay, if I make the last node's next point to my head node, then this becomes a circular linked list. So we know that in the singly linked list that we first studied, the last node's next pointed to null, but in a circular linked list the last node's next points to head node. Alright, and this could be in a singly linked list, this could also be a doubly linked list, okay, where we have a link to the next node as well as the previous node. That means in a doubly circular linked list, the head node's previous would be pointing to the last node. Okay, so because this is forming a circle, that's why it's called a circular linked list. Now what are the advantages of using circular linked list? First of all, you can start traversal from any point in my circular linked list and still, you know, you can traverse through all of the nodes. Also in circular linked list, the advantage comes when we want to traverse our linked list multiple times. Okay, so if it's a normal singular linked list and we want to traverse it, we take a temp pointer and we use it to traverse till the last node. But in case I want to traverse the linked list again, I have to come to my head node and then traverse. But here in a circular linked list, from the last node itself I can reach to my first node. Okay, so in those cases where we want continuous traversal of our list, in those cases circular linked list comes to our rescue. Now coming to the implementation of circular linked list, let's talk about the node. So the node here, the node structure that we see, okay, in a single linked list, let's talk about single linked list first. In a single linked list, we've seen every node will have two parts. First is the data part where we're storing some value, and the second part is the next, which is a pointer to the next node in my list. So will the node structure change here in my circular linked list? No, the node structure will remain the same. If it's a singly linked list, it will be this. If it's a doubly linked list, then we'll have an additional pointer previous. Okay, so no change in the node structure, just one change would be there. The last nodes next would be pointing to my head node. Okay, so let's see how we're going to implement this in code. First of all, creating class node here, and this will be similar to what we have already seen. It will have some int value, okay, whatever value we want to store in each of the nodes, and we'll have a pointer to the next node. So for that, we'll have node star next. Okay, and let's also create the constructor here for the nodes. If I'm passing any value d, I want that value in my variable, and then the next should be initialized with null. The next pointer is initialized by null. Okay, so this is my node class, and I can use this to create my circular linked list. How can I do that? Let's first create a head. Let's first create some nodes. Okay, so for example, I create n1 is equal to new node with value 1, node star in 2 is equal to new node 2, and I can make n1's next point to n2, and I can make n2's next point to n1. So in this case, you can imagine the n1 pointing to n2 and then the n2 pointing back to n1. So it's a circular linked list with 2 nodes. All right. Let's move forward and see how can we traverse a particular circular linked list. So this might change a bit. Let's first discuss what we were doing in a singly linked list. So when we were talking about a singly linked list where the last node's next was pointing to null, what we used to do was we used to create a pointer, temp pointer we used to call it, and start it at the head node. From the head node we will keep moving the temp pointer till it reaches null. Okay, when it reaches null, we would know that our linked list has ended here, so we'll end the loop. Here, in case of circular linked list, we do not have this null. Okay, what we have is the last node's next pointing to my head node. So what I'll have to do instead, I'll have to check if my temp node reaches my head node again. Okay, if I start my temp pointer at head and while traversing, I reach my temp pointer reaches to the head node once again, that means my entire linked list has been traversed. All right, so that will be our stopping condition here. Let's write a function void traversal, okay, where we'll be passing the head of my linked list, of my circular linked list. So what we'll do is we'll first of all create a temp pointer starting at head, and instead of using while loop here, we'll use the do while loop. Okay, so inside the do while loop, we'll check until my temp is not equal to head. I will keep printing the value of temp, and I'll keep moving my temp pointer forward. Okay, why am I using a do while loop here instead of a while loop? Because I want first this to get executed and then it to check if temp is not equal to head. Okay, if I used a while loop here, then because temp is initially equal to head, it would have never executed the loop, right? And in the end, let's just print an end line. If I call traversal for the current circular linked list, let's create a head pointer as well here, and we'll make it point to n1, and we run this. We get 1 and 2 are the nodes in our linked list currently. Okay, and if you want to basically see if this is actually a circular linked list that we are talking about, we can create another function, traversal in loop. Okay, just to show you that this is actually a circular linked list that we have created here. And what I'll do here is I'll add a counter while, let's say, it prints the nodes 10 times. Okay, so while k minus minus, I'll do this exact same thing. I'll print the temp value and I'll move the temp to the next node. Okay, and print an end line. So if I do traversal in loop, what will happen? I'll see 1 2 1 2 1 2 getting printed repeatedly, right? Because 2 is pointing to 1, then 1 is pointing to 2, then 2 is pointing to 1, and so on. It goes on and on. Okay, so you can now imagine how a circular linked list works, and you can see how we can traverse in it. Of course, we don't want to traverse the circular linked list in loop right now, but just for you to imagine how this will look in code. Okay, now let's move forward and see insertion. How do we insert an element in a circular linked list? And we'll focus really on how this is different from the insertion that we have already seen in singly linked list and doubly linked list. So if I have here a circular linked list and I want to insert a new element at the head position. So what I'll do is, first of all, I'll create my new node. Okay, and I'll have to move my head pointer to my new node, and also make my, first of all, make my new node point to the head node, and then move my head pointer to my new node. But there's another thing that I'll have to change here. What? That is this link, right? So I'll have to make, because I'm updating the head node here, so I'll have to update also this link which joins the last node to the head node. So what we'll have to do is we'll have to traverse, first of all, to the last node in my list. Okay, and then once I am at the last node, then I need to make its next point to my new head. First of all, we create a new node, we make its next point to my head, move the head pointer to the new node, and also we change the last node's next point to my new head. Let's see the code for this. Void insert at start node star head and the value that we want to insert in our new node. So first of all, let's create the new node, node star new node with the given value. And once we have that, firstly traverse to the last node and change its next value. Okay, and for that we'll create a temp pointer starting at head while temp's next is not equal to head. And when will temp's next become equal to head? When we are at the last node. So while this is not true, we'll keep moving our temp pointer forward. And now our temp pointer is on the last node, so we'll make its next pointer point to my new node. I'll make my new node point to the current head, and the head pointer will come at my new node. Okay, so this here we're changing the link from the last node to the head node. Here we're making the new node point to current head node, and here we are updating the head node, which will become our new node. Also, before we start traversing to the last node of our list, let's first check if this current list only has one node, or let's check if this list is empty. When we're trying to insert, if we're trying to insert the first node in my list, okay, that means head is null. In that case, I'll just say head is equal to new node and make the heads next point to head, because there's a single node, its next will point to itself, and I'll return from here. Okay, let's test this. So if I do insert at start head 3 and do a traversal, so I can see 3 got inserted, right? And let's say if head is equal to null and 3 is the first element that I'm trying to insert, let's see what happens then. Let me comment this out. So I can see that it works if I'm trying to insert the first element when head is initially null. That is our code for inserting at the start, and the time complexity for this would be O of n, right? Because we have to traverse to the last node of our list. Let's move forward and see inserting a node at the end of my list. So here again, if we have a circular linked list where the last node is pointing to the head node, first of all, to insert, we'll create a new node, right? And we'll have to get access to the last node of my list so that I can insert the new node after it. So we'll create a temp pointer and use it to traverse to the last node. In temps next, we'll put the new node, right? So this link will get removed. In my new nodes next, I'll put the head. Okay, so again here we'll have to update the link between the last node and the head node, because the last node here is changing, and the time complexity here again would be of n, because we need to traverse till the last node of my list. So let's see the code for this. Void insert at end node star head and the value I want to insert. So first of all, let's create the new node. It's equal to new node with the value that is given to us, and I'll add the same check if my head is equal to null, meaning if my circular linked list is empty right now, then I'll just add head is equal to new node, heads next will point to head, and I'll return from there. Otherwise, I'll make a temp pointer starting at head, and I will traverse this till it reaches the last node. So I'll add a check till temps next is not equal to head. Till then, we'll keep moving our temp pointer forward. When temp reaches the last node, in front of temp, we'll put the new node. And in new nodes next, we'll put the head. All right, so we've added a node at the end. Let's test this. Insert at end, where we are trying to insert 4 at the end of my list, and I also call the traversal function here for my head. Okay, we did not change this back to n1, that's why it was throwing an error. So this was our list, and we added 4 at the end of my circular linked list. So this was insertion at start and end. I am not discussing insertion at the middle, because that would remain the same as what we had seen in singular linked list, right? The change in circular linked list, the difference in the circular linked list comes when we're talking about insertion or deletion at the end of my list or at the start of my list, right? So if we're talking about updation at some kth node, insertion or deletion at some kth node, that will remain the same as we have seen before. Okay, so let's discuss now deletion. What happens when you try to delete a node from the start of my circular linked list? So this means I am trying to delete my head node. In this case, firstly, what we should do is make the node that needs to be deleted pointed to by a pointer. So let's say temp is pointing to the node that is to be deleted. After that, I need to change this link, right? Because this link points to the head. The last node's next points to the head. Now head will get updated because head is getting deleted. So I need to update this link as well. For that, again, we'll have to traverse to the last node. Let's use a pointer called tail to traverse to the last node of my list. And then I can change this link and I say, okay, now make the tails next point to heads next, and then I can move my head pointer to heads next. Once I've done that, then I can free up my temp node. The time complexity here would be O of n because I'm traversing till the last node of my circular linked list. So let's see the code for this. Void delete at start node star head. So first of all, let's say, okay, the node that needs to be deleted is my head node, and to traverse to the last node, let's create another pointer tail. So while tail next is not equal to head, we'll keep moving the tail pointer forward. Now my tail is pointing to the last node of my list. Once it reaches the last node of my list, then I'll make its next point to my current heads next. I'll move my head pointer to heads next, which will be my new head, and finally I can free up temp. I can also add a check here. If my head's next is equal to head, meaning I only have one node in my list, okay? If there is no node, okay, if my list is empty, then I can simply return, okay? If the list is empty, I don't need to delete anything. But if my node has if my list has a single node, okay, in which case I can test by checking if heads next is equal to head. If this is the case, then we can just free up my head node and return from here. Okay, I don't need to do anything else. So let's test this. Delete at start, and let's see the traversal after it. So right now I have 3 at the start of my list, and we can see it got removed, it got deleted from my circular linked list. Okay. Coming to deletion of a node from the end of my circular linked list. So again, I have a circular linked list and I need to delete the last node. I need to delete the last node. So in order to delete the last node, we'll have to make changes to the new last node. After I delete this node, what will be the new last node? That will be this second last node. Okay, so first of all, let's call this second last node. Okay, we'll use a pointer second last to point to this, and this will be my last node. So last node is the node that I need to delete. Once I have reached to the second last node, I will change its link, its next link, to point to my head, and once I've done that, then I can easily free up my last node. Okay, and again here the time complexity of O of n because we're traversing till the second last node of my list. So delete at end node, star, and head. Okay, the initial checks will keep the same. If my head is equal to null, if it's empty, will return. If heads next is equal to head, if there's only one node, in that case we'll just free up the head and return. Else we'll create a pointer. Let's create a pointer second last starting at head, and while second last next is not equal to head. So when I reach the second last node, its next will be equal to head. Till then, I'll keep moving this pointer forward. Once I've reached, I'll create another pointer for the last node, which will be second last node's next. I'll make the second last node's next point to my head node, and then I can free up my last node. Okay, let's test this. Delete at end. Traversal. Okay, so now here we can see 4 got deleted from the end of my list. Okay, so that's how we delete a node from the end. We've seen insertion, we've seen deletion, and we've particularly seen how to handle these operations when there's an operation happening at the start of my circular linked list or the end of my circular linked list, because that's when you'll have to keep in mind that okay, this is a circular linked list and I need to make the last node's next point to my head node. Okay, great. Let's come to a coding problem now and try to solve a coding problem on this topic, circular linked list. What does the question say? The question says we are given a circular linked list and we need to split it into 2 halves. Okay, and if there are odd number of nodes, then first list should contain 1 extra. Consider this is a circular linked list that is given to us, and we need to split the circular linked list into 2 circular linked lists. So the output would come out to be something like this. Okay, and this is in case of even number of nodes. If we have odd number of nodes, something like this, in that case what should be done? The first half of the list should contain 1 extra node, right? So in that case, these will be the 2 circular linked list, okay, the 2 halves of the bigger linked list. In order to divide this linked list, the circular linked list, into 2 halves, we need to know what is half of the circular linked list, and for knowing the half, we need to know the middle point of my linked list, right? And now if you remember, we did discuss how to find the middle point of a linked list. We did that using slow and fast pointer approach, where we said that if the slow pointer is moving by 1 node and the fast pointer is moving by 2 nodes, then in the same time, slow pointer will cover half the distance as the fast node, right? So if the fast node reaches the end of the list, at that time my slow pointer will be at the middle of my list. Make sense? So if I have my slow and fast pointer starting from the head and I move my slow pointer by 1 node and fast pointer by 2 nodes, when my fast pointer reaches the end, the slow pointer will be at middle. Let's see that. In the first iteration, we'll have my slow at 2, fast at 3. In the next iteration, I'll have my slow at 3 and fast at 5. So now here you can see fast has reached 5, which is the last node. In that case, I can say that my slow pointer is now at the middle of my linked list, which is at 3, right? So from here, I need to divide my list. Now I need to divide my list into two circular linked lists. To divide it into two circular linked lists, let's create the heads of those two circular linked lists. So the head of the first circular linked list would be at the original head. Let's call it head 1. And the head of the second circular linked list would be at the next of my slow pointer after my middle node. So let's call that head 2. Okay. So now I have the heads, the starting point of my two circular linked lists. Let's now decide what would be the last node of these two circular linked lists. So for the first list, for the first half of the list, the last node is the middle node, which is being pointed to by the slow pointer. So what we'll do is we'll change this and we'll say make the slowest pointer next point to my head 1. Okay, so I have my first circular linked list here, and similarly I'll say make my fast pointers next point to head 2. So I have my second circular linked list here. So I've divided my circular linked list into two circular linked lists, right? Again, if we have even number of nodes, let's say something like this, what will happen in this case? If I have my slow and fast pointer here, in the next iteration, when slow reaches here, fast will be at 3. When slow reaches 3, fast will be at 5. Now, in case of even number of nodes, we will stop when fast pointer reaches to the second last node, because after this it will come back to my head node, and I don't want my fast pointer to come back to my head node. So I'll stop here. Now, when fast has reached the second last node on the last node, we will stop and we'll say, okay, now my slow pointer is at my middle node as it is here. So we'll define our two heads. Head 1 will be at original head, head 2 will be at the node after slow pointer. We'll make the slow pointers next point to my head 1, and for the last node of the second list, we'll first of all move my fast pointer to the last node, and then I'll say, okay, now make the fast pointers next point to my head 2. So again, I have my two halves of the list here, right? And the time complexity here of this solution would be O of n, because we are using, we are traversing the entire linked list to find the middle node, right, using my slow and fast pointers. So let's try to implement this now. Let's create an input list for us. Node star head is equal to null, and we'll use the insert at end function to insert some nodes in my circular linked list. Let's see what this linked list looks like. Okay, so to divide it into two halves, let's create two new heads, head 1 and head 2. Okay, and this head 1 and head 2 should be pointing to the head nodes of the two circular linked lists. That would be the halves of this circular linked list over here. So let's create a function split linked list, where we'll pass the head of the original linked list and we'll pass the new heads, head 1 and head 2. And after we have solved this, after we have our head 1 and head 2, our two circular linked list, that will be the two halves of the original linked list, we'll call the traversal function on it. Okay, so let's now write our function split linked list. The first is the head of the original linked list. Second is the head of the first part of the linked list. And by the way, the original head and the head of the first part of the linked list will be the same, right? So You can either keep it the same or you can create another, pointer for it if you want, for clarity. All right. So the first thing that we do is we find out the middle node. Okay. Finding the middle node. So for that we create two pointers, slow and fast, starting at the head node. While fast's next is not equal to head, meaning it is not the last node, and also fast next is not equal to head, meaning it is not the second last node. Till that time, we'll keep moving slow pointer by one node and we'll keep moving my fast pointer by two nodes. Alright, so now my slow pointer is pointing to the middle node. So let's define the new heads, placing the new head pointers. So head 1 will be at the original head and head 2 would be at the next of the slow pointer. Also, in case of even nodes, we will move the fast pointer to last node. Okay, we can check if fast next is equal to head, meaning it is at the second last node, then we'll just move the fast to its next node, which will be the last node. Okay, now we are making the last nodes point to the head nodes. So the last node of my first half of the list would be pointed to by the slow pointer. So I'll say slow's next should be head 1 and fast next should be head 2. For edge case, we can keep a condition if heads next is equal to head, meaning there's only one node, then we won't do anything, we'll just return. Okay, we can say head 1 in that case is equal to head and head 2 will just keep null and return from here. Okay, this is if list only has one node. Okay, so let's try to run this. So you can see this was my original list and these are the two halves of the list, 1, 2, 3, 4. And let's also check for odd number of nodes. If I add another node here, 1, 2, 3, 4, 5, then my first half of the list is 1, 2, 3 and the second half of the list is 4, 5. Alright, so our code works perfectly. Moving forward, we will be looking at lists in STL C++. So what is STL here? STL stands for Standard Template Library. It is a library of template classes in C++ which has implementation of the commonly used data structures and algorithms. And list is one of the template classes that is present there. Alright, so we can say that list is the template class in standard template library for doubly linked list. Now what this means for you is that whatever we've seen, right, how we create a class node, we define what are the properties of the functions, we wrote all of the insertion, deletion, updation, reverse functions for our doubly linked list. All of those functions, all of those implementation is built in and given to us by this STL library in C++ that we can leverage in code. So list is a template class for doubly linked list. Okay, doubly linked list where every node will have access to its next node and its previous node. Now if I want to use this list in my code using STL, what do I do? First of all, I need to include the list header file. Hashtag include list. Okay, this list will allow me to create a list and also use all of the functions on this list that are built in. And if I want to create a list, I can specify list, the data type of the values that I want to store in the list, and the list name. Okay, so it's as easy as saying list int L1. This will create a list for me called L1, a doubly linked list called L1, in which I can store integer values, and I can also initialize it at the same time by putting some values in my curly brackets. Okay, so it is that easy to create a doubly linked list in code using STL. Now you might be wondering, if it is so easy to do this, if it is so straightforward, why did we go through all of these previous videos and saw how to implement doubly linked list and how to implement all of the operations on it? That is really important, because once you understand how doubly linked list was actually working, that's when you'll understand how list in STL works. Alright, and number two, when you're going for interviews, DSA interviews, the interviewer might ask you to actually implement the doubly linked list and not just use the list present in C++ STL. So you should be knowing the implementation of singly linked list, doubly linked list, and all of the operations. But if you are given a problem and if you're given the freedom to use any data structure that you want, and you're looking for something like linked list, this list can come to your rescue and you can use it without without implementing the functions. A lot of these functions we'll see right now in this list are implemented, they're inbuilt inside the C++ library for us to use. Let's look at first of all some of the iterator functions that we have on our list. So the first one here is begin, and what begin returns is an iterator to the first element in my list. Okay, now what is an iterator here? Iterator you can understand by thinking of pointers, just like we talked about pointers. So they are pointer like, and what iterators do is they help us to access the elements of a particular STL container. Okay, so list here is an STL container, a container which is being used to store some values. Okay, and to access the elements or the values that are being stored in this STL container, we make use of iterators. Okay, not just list, we use iterators in other STL containers as well. Could be stack, queues, vectors, sets, etc. Begin function will return me the iterator to the first element. So if I have a list 1, 2, 3, 4, and this is a list L1, and I say L1 dot begin, then this will return me an iterator to the first element, which is 1. Okay, it will not return me 1, but an iterator to 1. So to access it or to print its value, I'll do star iterator. Okay, if I am writing iterator is equal to L1 dot begin, then to print the value of iterator, I will print star iterator to access the value that this is referring to. Okay. Similarly, end will return me an iterator to the position after the last element, after the last element. So if I have a list 1 2 3 4, L1 dot end will return me an iterator to the position after my last element, not to my last element but the position after my last element. Remember that. Similarly, we also have r begin and r end functions. What they do is r begin will return me iterator, or let's say it will return me a reverse iterator to the first element in reverse iteration. What do I mean by that? So again, if I have a list with 1 2 3 4 values and I ask for L1 dot r begin, then this will return me an iterator to 4. Okay, so basically r begin will return me an iterator to the first element in the reverse iteration. When I iterate this list in the reverse manner, what would be the first element? The first element would be 4. So that would be returned to me by L1 dot r begin. And r end, what this will give me is, this will give me a reverse iterator to the position after my last element in reverse iteration. Again, so if this list is reversed, what would be the last element? 1 would be the last element. So r end, L1 dot r end will return me an iterator to the position after the last element, which is 1 in this case in reverse iteration. Okay, so these are some of the iteration functions that we'll be using to iterate. One last iterator function is advance, and this is used to move my iterator. So in the advance function, I pass the iterator and I pass n, okay, some integer value, and what this will do is this will move my iterator by n places. So for example, in my list 1 2 3 4, I have an iterator to 1, okay, called ITR, and I say advance ITR by 2 steps. So this will move my iterator to 3. Okay, let's look at these functions in code now for better understanding. To create a list, we've included the header file for list, and now I can create a list of type int with some integer values. Now if I need to access the first element of this list, I can use an iterator. Now how do I get an iterator or define an iterator to this list? I can either say list int iterator and the iterator name L1 dot begin. Okay, so either I can mention the iterator data type like this, I can mention the iterator and what type of iterator I want. I want an iterator for this type, list of type int, or I can just say auto iterator in this case also, because this is, I'm saying this is equal to L1 dot begin, so it will be able to derive that this is an iterator for type for a list of type int. Okay, and to print its value, I can say star int so you see 1 got printed here because that is the first element of my list. Now suppose I create a reverse iterator. Okay, let's call it a reverse iterator L1 dot R begin. So this will give me an iterator to the first element in the reverse iteration. That means 4. Okay, and if I print this, what is getting printed? 4 is getting printed, right, as it should be. I can also try to move my iterator. So if I say advance my iterator by 2 steps, okay, so now if I print, let me comment this out. Now if I print, my iterator is at star iterator is printing 3 because my iterator now has moved from 1 to 3, right? So I can use the advance function for that. Next, let's discuss how do we traverse a list, okay, and let's see this in code directly. 2 ways to traverse a list. First is range based or loop based. So what we do is in the loop we basically use a for each loop. So for auto number in my list 1, print num. Alright, and let me comment out the above code. Okay. So you can see 1, 2, 3, 4 got printed here. I was able to traverse and print all the values of my list. So this is the range based way to do this. Another way to do is through iterators. Okay, and how do we do that? For that we use a for loop. So for auto iterator, which will begin at L1 dot begin, the first element, and this will go on till my iterator does not reach L1 dot end, which will be the end of my list. Okay, this is the position after the last element of my list. ITR plus plus. So I created an iterator to traverse my entire list from L1 dot begin to L1 dot end, and I will print star ITR here. So you can see again here we are able to see the traversal of my list. We can also traverse it in the backward direction. How can we do that? For that we just need to change this from begin to R begin and from end to R end. So now it will traverse in the reverse direction. Okay, let me run this and you can see here 4, 3, 2, 1. This is the reverse direction of my reverse traversal of my list that I've created. Let's talk about inserting elements now. To insert elements, we have a function called insert. Okay, if I want to insert any value into my list, and in the insert function we pass the iterator and the element. What this does is this will insert the element before the iterator. Okay, so if I have a list 1, 2, 3, 4, okay, and I say L1 dot insert, where I'm passing an iterator that is pointing to 3 and I'm passing the element as 5. What this will do is this will add 5, insert 5 in my list but just before 3. And I can also pass another parameter here in this function just called count. If I pass count, by default this is 1. If I pass any value of this, then it will insert that many number of elements. Okay, so if I'm passing iterator to 5, so this will insert 5 2 times for me before 3. Okay, and another way to insert is when I want to insert a range of elements. So there I can pass a start iterator and an end iterator. What will happen is, suppose again I have a list and I have my start iterator here, S iterator, and I have my end iterator here. So what this will do is it will insert values starting from start iterator to end iterator, but not including the end iterator. Okay, exclusive of the end iterator. This will insert this value, this range of values before the iterator that I pass. Okay, let's see this in code. Inserting elements. So if I say L1 dot insert, let me first create an iterator. So I create an iterator at starting at L1 dot begin, and then I advance it by 2 steps. Okay, so now it is pointing to 3, and then I say L1 dot insert the iterator and the element that I want to insert, which is 5. Let me print the values again. So you can see here 5 got inserted just before 3 because I passed an iterator to the value 3. If I add another parameter 2 here, I pass the count here, so this will insert 5 2 times for me. Alright, and here if I pass 2 iterators, a starting iterator and an end iterator. Let's say I pass or start iterator L1 dot begin, and I pass an end iterator L1 dot end, or let me advance it from begin. So I'll move my advance, using advance I'll move my end iterator to 3. Okay, and here I'll pass my start iterator and my end iterator. So let's see what happens. So I passed a start iterator that was pointing to 1 and end iterator was pointing to 3. So from start to end, not including the end element, this will get inserted, meaning 1, 2 will get inserted just before 3. Okay, so this is how I can also insert a range of values in my list. Moving forward, we can also delete elements using erase function. So in the erase function, we pass the iterator and that element to which the iterator is pointing, that will get deleted. So if I have a list and an iterator to 3 and I say L1 dot erase iterator, this will remove 3 from my list. In the erase, I can also pass a range of values using start iterator and end iterator, just like we saw while inserting. We can pass start iterator and end iterator. This will erase values or elements from start iterator to end iterator. Okay, this means this is not including the end iterator. Okay, so excluding end iterator value. Okay, let's see this in code. So if I'm saying L1 dot erase, Okay, and again I'm passing the above start iterator and end iterator that we defined, and print the list again. So let's see what happens. So I passed in start iterator at the end, and let me actually move this below so we're able to see this. Okay, let me rename this, or let me get rid of this. Okay. So you see here what happened was 1, 2, 3, 4, this was my original list, and I passed a start iterator at 1 and an end iterator that was pointing at 3. So from 1 to 3, not including 3, so only 1 and 2 got deleted from my list. Similarly, if I pass just one iterator here, for example, I just pass the start iterator, what will happen in that case? Just the first element will get deleted, 1 will get deleted. Okay, so this is how we can insert elements, delete elements, traverse elements in my list. And there are a couple of other functions as well, member functions for list. For example, the front function returns the value of the first element if you need the first element of my list. The back function returns the value of the last element. Push front will add a new value to the start of the list. Push back will add value to the end of the list. We've seen all of the operations for this. Pop front will remove the first element. Pop back will remove the last element. Size will return the size of the list. Empty returns if the list is empty or not. So 1 if the list is empty, or else 0, and reverse is used to reverse the list. So most of these operations we have seen, we've actually implemented these ourselves for linked list, but these functions are inbuilt which we can use directly when we are using STL. So although you won't find a lot of even practice questions on C++, on list STL in C++, but just for the fun of it, you can try some of these functions. The questions that we've already done, we've seen in linked list, you can try a few of them out using STL. But remember this, in your interviews, in your DSA interviews, you will be asked, most probably you will be asked to implement the linked list. So remember how to implement it and all of the implementation of all of the operations that we have seen so far. Amazing. Thank you so much for watching this, and that's all for this video where we covered circular linked list and we covered list STL. And that's all for this video. Thank you so much for watching. Do practice all of the questions that we discussed in this module, and if you have any doubts, drop them in the comments so that we can get to them.